Hi, everyone. We're just waiting a minute or two to let people join. We'll get started in just a moment.
And just a couple of housekeeping. The chat is disabled. If you have any questions, please put them in the Q&A and we'll try and get those answered throughout the course. Um, yeah.
Hello, everyone. Good morning, good afternoon, good evening, everybody. We are excited to do our information in a photon course in the CQN Winter School 2025 edition. I hope all are joined and have settled in. Just go through the journey of a photon through a information channel and try to see what can we do to the photons before we actually measure them and get the maximum information out of it. The prerequisites for this course are basic complex numbers, basic probability theory, very basic linear algebra, and some quantum mechanics. And the goals. We will discuss what are known as the coherent states of light, then some modulation formats, some detection methods, and what constitute a channel and what is channel capacity. Also, we'll try to compute the capacity of a few channels which we use, which are some very common channels, information channels. And one thing to notice here, or I would like to stress, is that we are talking about sending classical information through a quantum channel. Okay, so we use the quantum properties of light to send classical information. So this is not a course which develops quantum information sent through quantum channels. It is classical information sent through quantum channels, and what are the limits and what are the capacities. All right. Basically, we want to send a message. Let's say we have some very cheesy message to be transmitted through a channel. So we have a message and we want to transmit it through. There is a transmitter, and the transmitter converts or modulates the messages and converts it into a physical medium, let's say some form of light or electromagnetic wave, and then that gets sent through a medium. If you're using a mobile device, it is the medium is our atmosphere, and then there is some noise getting into the medium, and receiver receives a signal and it decodes, okay, and tries to give you the same message which the person sent you. You want to receive the same message. You don't want to change the message when it reaches you, right? So this is the basic setup of a information channel. And we are going to, as I discussed earlier, we are going to use the quantum properties of light to improve our capacity, how much information we can send, how to send it, and how to receive it, okay? Uh, yeah, as we discussed, quantum properties means light is quantum means that if you try to measure the light, you lose all the information you have, okay? And so if you want to do anything in this network to improve your capacity or improve the amount of uh, data you can send over the channel, then you should do something before you actually measure it. Okay, so the quantum properties of light collapses once you measure, because of which you have to do something. If you want to do something, you have to do it before this stage where the receiver makes a detection. So that's what we are going to concentrate in this talk. Okay, what is the basic setup we have? We have the pure state, okay, which is written in the Dirac notation ket c. Okay, this is just a complex number for complex number or a complex vector. Okay, for the time being, it's a pure state is represented like this, and it's a unit norm, and the scalar product of c with c itself, that is the norm of the norm square of the unit vector, that is 1. And this is the Bra and Ket notation of Dirac. That's what we use in throughout this lecture. And one example of a two-level system, that is a 1-qubit system, is a two-dimensional complex vector space. And let's take some orthonormal basis of your space. Let's say this is the number 1 0, and this is number 0 1. Okay, or the other way. You can fix anything, and then that's a basis for the orthonormal basis we fix, and then any complex number of unit vector, unit norm, can be represented like this, where mod alpha square plus mod beta square is equal to 1. That is a general vector we have, and this is a quantum state for us. And some other basics which we need is from probability theory, and we want to know what is a discrete probability distribution or an random variable. A discrete random variable takes values in 1 0 1 2 3 etc. This is a function from your sample space to the number 0 1 to up to infinity z plus v, right? And an example, okay, that should satisfy what? That should satisfy the total mass should be 1, right? And the Poisson distribution is an important example for us. The Poisson distribution is pk at k, the probability of k is e to the power minus lambda to the power k divided by k factorial, for some fixed lambda. Okay, lambda is a fixed number, and the probability of k is e to the power minus lambda to the power k divided by k factorial. This is the Poisson distribution. And the mean of the Poisson distribution, if you just sum it up by multiplying with k, you can see that it is lambda. And the variance, if you just do this thing, and k minus expectation is the mean, the whole square times pk, the probability, that is also lambda. So Poisson distribution is a very nice discrete distribution for which the mean and variance are the same number, lambda. That is the Poisson lambda distribution. Okay. So I believe it's clear that lambda is a fixed number, and with respect to that number, we can define a Poisson distribution by prescribing the probability of k to be this one, and mean and variance of this distribution is going to be just that lambda with which we started with. All right, now let's look at some continuous random variable. Our main example, or the only example which we deal with in this talk, are the normal distributions. Okay, this random variable takes value in minus infinity to infinity. That's a real function, real valued function. And the probability distribution here, if here it was a summation is equal to identity, summation of the probabilities. If here the integral of the probability density function or probability mass function should be 1, and that function in the Gaussian setting, it is this function. This is the exponential of a quadratic. Okay, e to the power minus x minus mu the whole square divided by 2 sigma square, where mu and sigma are some fixed real numbers. Okay, and this is the normalizing constant, and in this case we have a normal distribution with mean mu and variance sigma square. These are some basic facts which we need about this setting. And there is an important theorem which we need. In this case, we also say that x follows normal distribution n mu sigma square. Here we say k follows Poisson lambda. Here we say x follows n mu sigma square. And one important theorem, which is a special case of the central limit theorem in probability theory, is that when lambda is very big, Poisson distribution is almost like a normal distribution, or Poisson converges to normal when lambda is big. And what normal it is? Normal should be prescribed by two numbers, mean and sigma square, and the mean is lambda and sigma is also lambda. So as we discussed earlier, Poisson has the same property, like Poisson has a mean lambda, Poisson lambda has mean lambda, and variance also lambda. Same thing, this will converge to a normal with mean lambda and variance also lambda itself when lambda is quite large. This approximation we will use in this talk. So please, if you have not seen it earlier, please note it down or keep in mind. Poisson lambda, when lambda is large, can be approximated using normal distribution with same lambda as the mean and variance. Okay. If you want to see a little bit about this approximation, you can go to this website at your leisure. Not now, maybe I will share the file with you, and you can see a cool demonstration of this thing. So we talked about distributions, discrete and continuous. We talked about quantum states first, and now we want to discuss what is a measurement. A quantum measurement. The measurement which we use in this talk are known as the von Neumann measurements or projective measurement of a one state. This is, by a measurement, what we mean is an orthonormal basis of the Hilbert space we start with. Okay, this has to be fixed in your mind for throughout this talk. We are going to repeatedly use the notion of a measurement. A measurement means an orthonormal basis of the inner product space or the Hilbert space you start with. And this has that what is an orthonormal basis? It's a set of, it's a basis first of all, and they are all orthogonal to each other. Okay. And if you have any state C, which is a pure state or a rank or normal norm one vector, then that pure state determines a set of probability vectors. So that is the absolute value of omega k with C. If C is your vector, the absolute value of omega k with C, the scalar product of omega k with C, that these are the probability amplitudes, and absolute value squared, that is the probability of the outcome k. Okay, the kth outcome is obtained with respect to this probability pk. If you have a orthonormal basis, you can always expand your vector C using under this basis, and the measure basis is like this. Okay, the vector C is going to summation. I'm sorry, it is not actually pk. There's a typo here. This is omega k C. Okay, so it's not pk, but it is scalar product omega k with C. And let me try to change it now. It's here. Oh, it will take time. Okay, so I'll change it later. So just know that the vector C can be written as scalar product omega k C with omega k. That is how you can expand a vector with respect to orthonormal basis. So in our language, if you have a measurement omega k, there is a expansion of the state C in that measurement. And the idea is, the basic idea with which you should keep throughout this it arises from quantum mechanics, which we should keep throughout this talk, is that the probability of when you measure C in the basis omega k, or in the during the measurement with the measurement omega k, the kth outcome omega k is obtained with the probability pk, which is the absolute value of omega, the scalar product omega k C the whole square. That's the basic quantum mechanical fact which we are going to use. Now I will leave it to Jack for discussing some modulation formats, and we'll come back after that.
Yeah, thanks, Tiju. Give me 1 minute to share my screen here. Let's get the laser pointer turned on. Okay. Tiju, can you confirm that you can see my screen?
Let me see. I am not seeing your screen. Yeah, wait a moment. Yeah, I can see your screen. Very good.
Right. All right, everyone. So my name's Jack, like Tiju said. I am a PhD student at the University of Maryland. And now that we have kind of some background and necessary material to understand the context of which the rest of this conversation will happen, I'd like to motivate this course a little bit more, starting out with kind of a historical background and then going into some more details about how we embed that information into light signals. So information signals and mediums are critical to every part of life today. Everything from radio, which we use to transmit information with our phones, sound, which I'm using to communicate right now with this microphone and how you're hearing it, light waves, which we're going to talk a lot about in this case, and is really the future of a lot of high-speed information and deep space information communications, and all the way down to things like DNA. So like information is embedded in every part of our life. And it's important to consider when we're trying to transmit information rather than store it, we need to consider a few different things to find what is the optimal medium and what's the optimal system we can use. So some priorities, we want whatever it is that we're doing to be controllable. We want to have fine control and prediction or precision about taking our information and embedding it into the system. We want it to move quickly so we can transmit across large distances. We want it to be predictable so that way we can design things like error correcting codes and receivers and transmitters that will effectively transfer that information. And in most cases, we want it to be really energy efficient. This is especially relevant today as we have larger and larger data centers always being created to train these large AI systems. And so energy efficiency is becoming even more important just for transferring that information. And it can be as small as transferring it from one server rack to another, or transferring it across the country via fiber telecommunication lines, or all the way from some space-bearing system down to Earth and back. So the 20th century was really the beginning of the information age, starting with Claude Shannon's mathematical theory of information, communications, and then moving forward through all sorts of different devices and systems. So radio waves dominated the 20th century, and they still do today in the 21st century. These are electromagnetic waves with, we say long wavelengths, even though they go down to as small as a millimeter. And they have worked on things like classic transistor radios used in iPhones, all the way up to Mars rovers that are operating today. They're able to pass through most materials, which is of great benefit. It makes it ubiquitous across most situations. And it's just generated and read with electronics. So this is something that through the advance of silicon semiconductors and the mass manufacturing processes has allowed billions and trillions of transistors to be on individual devices and deployed across massive systems. And altogether, with the fact that it's an electromagnetic wave, so it travels at the speed of light, the system has really been ideal for most situations. And we've learned to use it as humans quite effectively. However, there are still some scenarios where we need to look beyond classic radio communications. So laser communications, also synonymously called optical communications, is becoming more and more common and really has been since the 1990s. So the laser was invented in the 1960s, late 50s into 60s, and it allows for light to be emitted coherently. So this is light that you have very fine control of, and it's a sort of quasi-classical state that we'll talk more about. But the wavelength is much, much shorter than radio waves, on the order of hundreds to thousands of nanometers. So typically we consider in optical communication systems a specific one at 1.5 microns. And this comes from the fact that the fiber optic cables, like the ones shown here, have an ideal transmission, or they have an ideal transmission at particular wavelengths. So this 1550 nanometer, which is the telecom band that's very, very common, is really pretty much exclusively due to the fact that we can make these fibers at incredibly low loss at that particular wavelength. But we're not limited to that. Lasers can operate at a whole range of wavelengths, and in different scenarios, there might be different use cases, but they can be very small. So in this case, this is a laser diode. So you can see that's smaller than a penny. Or you can make them large systems that are incredibly powerful using things like large crystals, like the first laser is built on a ruby crystal. And these solid state lasers can be incredibly precise in terms of the wavelength that they emit. And can operate at very, very high power. So in things like this Psyche mission, which is currently the furthest deep space optical communication mission ever attempted, they use a solid state laser for most of their communication. And so in the future, what we'll see is a continued drive towards optical communications as more and more of our internet sits on these fiber telecommunication networks that are below the ground and transmitting this data to you right now, as well as in applications like deep space, where the use of laser communication system allows you to use smaller wavelengths so you can transmit more information per second. So we're optimizing to make it smaller, cheaper, more power efficient, and to send more data in a given time frame. Now, I said that the light emitted by a laser is a quasi-classical field. And what I mean by that is that it really is an electromagnetic field. So it's an oscillating, quasi-monochromatic as well field. So in this case, you can picture that you have both an electric field and a magnetic field oscillating in some transverse plane as it propagates through space. And for the purposes of what we're going to consider today, we'll consider the light to be truly monochromatic. It's a single wavelength of light, and we'll say that it's 1550 nanometers, like I said earlier, which is the standard for telecommunication. Now, if I were to write out the field of this electromagnetic wave as it's propagating through space and time, I might write it in such a form. So I have my electric field E, which has both a spatial component R and a temporal component T. And also not included here, I'm assuming that it's a single wavelength, like I said, quasi-monochromatic, and that it has a definite polarization. So in this case, the E field is pointed in the positive X direction. In general, you can have light that doesn't have a polarization, so it can kind of be a mixed set of light that's has its E field pointing all over. But for our lasers, we're going to consider that this is a polarized field. So once I make those two assumptions, then I can write this field out. And I can say that I have this amplitude of E with both a spatial and temporal component, and it's oscillating at some center frequency omega naught. And it has this additional phase component phi. And I'm going to bound this field that I'm interested in over a specific time frame. So just like how this one is shown here, propagating in the Z direction, we can imagine that if I were to start at a single point, say 0, and then propagate forward in time instead of space to the end of this 3/2 of a wavelength, I would call that my time t. And now I will also consider that really the area that's taken up by this field, it has some transverse profile. So it's occupying some area A. And with quasi-monochromatic light, with a coherent state like we're considering here, one thing that's nice is I can split up the field into both its spatial component and its temporal component independently, and then still have this carrier oscillating frequency omega naught. So now, if I say that I choose light that I'm going to be interested in, I'm going to define now my polarization, my wavelength, or my monochromicity. I'm choosing a spatial profile, so I'm fixing this phi of r, and then I'm also fixing this temporal profile, this S of t. Then I've totally defined a mode of the electromagnetic field that I'll be interested in. And one thing I'm going to say here is now if I'm only going to look at one component of the field, look at just the E field, I can write this S of t as this amplitude E with this additional phase term. And keep in mind that the oscillating term is stuck here in this latter term. We'll call this a simplified square pulse. And the reason we're going to call this a square pulse is that if I just look at this E here, I imagine that if I took the mod square of this, it's going to be a constant value throughout. So the intensity of the field is remaining constant throughout this entire time. Going into a little more detail on this field, and this is just important as kind of background as we're going to work with these fields, these square fields for most of the rest of the talk. I want to give you guys a few properties to consider. So the same field that we were just talking about, if I draw it out here, you can see this flat top, which is representing the intensity like I was showing before. It's constant throughout this pulse from time 0 to t. And this is occupying a mode of the electromagnetic field. I'm going to now start calling this state alpha, written in Bra-Ket notation, with this alpha being a complex amplitude. And the reason that I can now put this in this Ket form is that I've defined my mode. So this is the mode that my quantized electromagnetic field is going to live inside of. When I make that distinction, I can start to write some things out that will help me characterize and easily represent these states. So what I'm going to show here is the phase space representation of the state, where I have two quadratures, the real and imaginary. And alpha is this point sitting at the center of this little sphere here. Oops. This is not a point in space. It's actually, this is an area occupied by the uncertainty of the state. So we won't go into too much detail, but keep in mind that as a quantum state, there's always some uncertainty in your measurement. So when I represent it here, it's not a point in space, but it has some area represented by its Heisenberg limited uncertainty. So S of t is still the field amplitude. And I can say that since I've defined it to be in the mode from 0 to t, that it has this amplitude E to the E, and then it's a phase term only in the frame 0 to t, and it's 0 otherwise. I'm going to now tie back to the relation of the Poisson point process that Tiju was talking about earlier, and I'll say that the rate as a function of time is the mod square of this amplitude. And so we'll call that lambda, which is just equivalent to E squared. So this is again saying that this is a flat top pulse, that this intensity or rate is constant throughout this time. An important distinction and something that we quantify often is the amount of energy present in this field. So in this case, a useful metric is the mean photon number, or the average number of photons present in that defined mode. And we will call that N for all of our slides moving forward. You can think about it as just integrating over your rates throughout your entire time of your duration. And in this case, for the flat top pulse, it simplifies just E squared times T. So this is a coherent state. It has a phase space representation. It has some rate over which it can produce clicks or produce energy or produce photons. And it has this average amount of photons, N. Now below is a phase space representation of two different coherent states, one characterized by alpha and the other minus alpha. So both of these states will have the same mean photon number because they're just a phase shift away. And so they carry the same amount of energy. But if I were to draw them out in this field representation, we'll see that this flat top pulse has, we'll call it a positive E, whereas the one that's shifted by a pi phase will have this minus value, minus E. So we'll see in a minute that this is a specific type of modulation where I could choose to send you a laser pulse with either of these two coherent amplitudes. In this case, it would be the binary phase shift keying. Okay, quick poll question. Let me see if I can learn how to pull this up. But I'll read it out loud and then I'll try and pull it up on the screen so you guys can answer. So which of the following coherent states has the highest mean photon number? And I'm giving a few different options here. One giving this mean photon number, another with a coherent amplitude, another with a rate, and another with another coherent amplitude. So think about it for a second and let me pull up the poll. Okay, it should be available to you guys. Hopefully you can see the poll. Oh yeah, I'm seeing some answers come in. Okay, I will let you guys answer that for just a second. Like we have about 35, so 30, 40% of people participating. So we'll see if we can get to 50 and then we'll call it there. Still going. Okay, cool. I'm going to end the poll. So we had a pretty close solution here. Let's see if I can share the results. So pretty close. We had a lot of people answering A and a lot answering D. The correct answer is D. So even though in this case, a lot of that is coming from this imaginary term, the mod square is going to be greater here than if I just put N equals 3. So all of this is really to say, well, this poll is really just to keep you in check here, but all this is to say that when we're considering these coherent states of light, they can be written in a few different ways. But when we make this assumption that it is quasi-monochromatic, it has a definite spatial and temporal profile, and we know the polarization, that we can start to make a lot of simplifications that make our life easier as we move down the road here. So let's see. There we go. Okay, so now that we know quite a bit about the field that we're working with, we're going to talk now about modulation, embedding information into the light itself. So the optical field is the one we've considered so far here. So it's this oscillating field over time. And what we want to do is embed information in it in one of two ways. We can either do it via analog modulation or digital. So analog is something you've probably heard of in the past. If you listen to the radio, AM and FM radio signals work this way. Their field is not an optical field, but it is an electromagnetic field. So an analog signal has some continuous definition that you want to embed into the field, and you use a modulator to physically transform the field that's transmitted. So an amplitude modulation, we are dampening the amplitude or the intensity of the optical field. And then in FM, we're changing the frequency. And so you can see this is a continuous change in the system, something that you would need to extract if you want to get the information out. And this is used in a lot of ways, but the thing that we're mostly interested in when we're saying communication is digital modulation. So this is where I have some set of digital values, in this case binary. So I want to embed these ones and zeros into my field. And so I have this optical intensity, which is constant throughout my field here. And I use a modulator. And in the case of amplitude modulation, I could do something like on-off keying, where I'm representing a 1 with the field staying on and a 0 with it turning off. Or I can choose to do a phase shift keying again and frequency shift keying. So with frequency shifts, it's the same thing as before, except for now, instead of this kind of continuous adjustment of the transmitted frequency, it comes in discrete chunks here. So each of these is meant to represent a binary value. And something like I showed before could be phase shift keying. So instead of changing the frequency or modulating the intensity, I can shift the phase. And the one shown here would actually be a binary phase shift key, like the one that I showed you on the screen just before. Oops. Okay, going into a little bit more detail, one example that's relevant specifically to deep space modulation formats is on-off keying or pulse position modulation. So in on-off keying and in pulse position modulation, during each time slot, where I have some little defined 0 to t. So imagine that each of these little slots is its own 0 to t, which is a channel use. I'm either sending the signal or I'm not. So either there is a present electromagnetic field or there's vacuum field. In the case of on-off keying, in every single one of these frames, I will either turn it on or off, and that will represent either a 0 or a 1, which is nice in some scenarios. But another option is to use pulse position modulation, where I send vacuum for all of my pulses except for a single slot. So if I have these M intervals and I send a single pulse here, the detection of this pulse, so a single photon detection here, would indicate what slot the photon arrived in, and I'm able to send more than 1 bit throughout this whole thing. So each transmission of a pulse position modulation frame can transmit up to log 2 of M bits. So if this is a 8 interval, or I guess this one's like 16, then this is a 4-bit transmission, whereas with on-off keying, I'm sending 1 each time. So it's just a single bit. The reason this is nice in deep space communications is that all I have to do is send a signal at a single time, wait for a single photon detection event, and then I can decode it. And we'll talk later about how we can quantify why this is useful for deep space. But just keep in mind that pulse position modulation is a really common modulation for deep space. In terrestrial communications like fiber, the coherent modulation schemes are much more common. So the general form of phase shift keying, where I'm adjusting the coherent modulation to choose a phase factor for each of my symbols, but I'm keeping the same amount of energy, is nice because I have a constant energy that's always present in my system. So I know what to expect there. The one that we're going to investigate quite a bit, and I've already talked about, is BPSK, binary phase shift keying, where I'm sending one of 2 signals, alpha or minus alpha, both carrying the same energy and both having these like flat top pulse structures. The more general is the Q array phase shift keying. So if I have an alphabet of Q possible signals, and I were to plot them in phase space, they would look like this. Even more common for things like fibercom is quadrature amplitude modulation. So these constellations can pack a lot more information density into a single transmission. So in this case, this would be 16 quams. So you can see there are 16 possible symbols that I could send during each of the transmissions. So imagine during each 0 to t, I would send you one of these signals, and then your job would later be to decode which one was transmitted to you. You can pack more information into this. In fact, you can get close to optimal, just because during each transmission you have a larger distribution of possible symbols to play with. And I won't go into detail of why this is here, but one thing that's important to consider is that the optimal distribution across all of your symbols is actually a Gaussian distribution. So if you imagine that this QAM was large, imagine you had not 16, but hundreds or thousands of them, and you could assign a prior probability or marginal to each of these possible symbols. Imagine a Gaussian that goes across this, right? So these symbols here with low energy would be transmitted more often than the ones that are further out in the plane that require more energy to transmit. So it's just an interesting fact, but yeah, QAM is much more common, but it's harder to generate in most scenarios just because you have to change both the phase and amplitude. And you might be asking, how do you change these factors? How do you do this modulation for optical fields? For coherent states, it's actually pretty nice. We have these very well-developed technologies called electro-optic modulators that use the Puckle's property of electro-optics to generate a phase difference in a waveguide. So let's look at this. So imagine that my light is coming in through this optical fiber here in yellow. And I'm going to split it here into two different pathways. So the light is half of it is going in one arm, half of it is going in the other. When I send the light through this half here that has these gray bars around it, I can apply a radio frequency to change the phase by inducing a local difference in the index of refraction in this arm here that will induce a relative phase. And then when they recombine, the two arms are recombined at the end here, what it will do is introduce an effective phase difference. And you can configure these in quite a few different ways. You can induce a phase difference. If you configure it the right way, you can choose an intensity difference. So you get this whole phase space where you can choose with a large enough system to change both the amplitude and the phase. And so your light that's coming in with just, a coherent flat top pulse over all arms, you can then output it with some sort of data. So in this case, we haven't said if it's going to be phase or amplitude, but imagine for simplicity that this is a binary phase shift keying here that you're choosing to modulate with your RF signals. Physically, these devices are usually made with things like lithium niobate, and they're quite small. So this would be, maybe 4 inches in length, something like that, a little bit smaller sometimes. And you have a fiber input and a fiber output, and then you have some RF signals that come in here. So these are really, really common for telecommunication systems in the internet today. And they're also useful in deep space communication systems for modulating your light. Okay, another poll question here. So let's say that I give you a communication system and I say, which of the following formats is the most challenging to generate? So I'm asking you to create one of these. Which one's going to be the most difficult to generate? So analog, 8 QAM, on-off keying, or 16 ppm. So, I see the poll is already up. So let's see how the answers come in. Again, we'll try to get 50% participation here, but we'll give it just a minute or so. Okay, answers are still coming through, but we're at about 60% participation here. So I'm going to end the poll and share the results. So good job, everyone. B would be probably the hardest here because we're changing both the amplitude and the phase. Now you might be thinking 8 is an interesting number here because it's not actually a common one. You're right, 16 would probably be more common, but 8 would actually be slightly simpler just because you would be eliminating part of the operation there. But yeah, quadrature amplitude modulation generally more difficult than the others. Now there's some nuance to this. You might say, well, maybe with QAM, I don't need to operate as quickly, or my modulation is slower because I'm packing more information into each pulse. yes, that's true. There's nuance to all this, but it's meant to be just an intuition of how hard is it to manipulate the light, regardless of how fast you want to do it. So good job, everyone. That is the right answer. Okay, so we now know quite a bit about the different modulation formats. So we know kind of how to embed information into the light. But we've said since the beginning that this is a classical quantum channel where I'm taking classical information and embedding it in a quantum system. And so far, we haven't said why this is a quantum system at all. Well, the coherent states, the states that we've been working with and the ones that are described by an ideal laser system are a quasi-classical state. They can be represented in a quantum form, just like all light can, but they come out to be a pure state when represented in the Fock representation. So let's go through that in a little more detail, and we'll see this kind of develop throughout the rest of the talk. So this same ket that we're looking at now defines a mode. So it still has its defined time, it has its defined spatial profile, and it has its defined polarization and wavelength. And I still have this complex amplitude alpha. But what I'm going to say is that this can be represented in a pure quantum state as a superposition of individual photon number states or Fock states. So these Fock states tell you, each number n tells you how many photons are present. And so you can imagine it's somewhat intuitive actually to think about. Like if I have this light that's coming to you and it's in a coherent state, and I put a photon detector there and I get detection events out, I'm only going to get a discrete number of photons that come out of it. And in reality, the state itself is a superposition of possible photons that you can measure. So it's not guaranteed to be 1 or 0 or 4 photons. It's a superposition of probabilities associated with each of the different photon numbers. And so when you write it out in the Fock basis expansion, you get each of these terms, which some of you might already be thinking this looks like a somewhat familiar term from some of the things Tiju talked about, and we'll see this pop up later. And so no need to memorize it, but yeah, we can represent our coherent state in the expanded Fock basis. Each of these is really just an infinite dimensional vector. So rather than the two-dimensional space that we started out with when talking about a qubit or an ideal two-level system, this is an infinite dimensional Hilbert space. So it makes it quite hard to represent these states in their true quantum form in a computational or numerical system. Just because you can't represent the infinite basis forever, right? So usually we have some cutoff. So if we have a coherent amplitude of say like 2 or 4, we're probably not going to need to represent the Fock number 1 million, right? The probability is going to be extremely low that we're going to get that. But this is the reason why we've been saying that this is a classical quantum channel. Is we're going to embed our classical information into the quantum state of light, which has this expanded representation. So what I'm saying down below here is basically the same thing. Recall that we have the spatial mode, this temporal mode, the oscillating field, and it has this associated mean photon number n, which is really the reason we're using n here. That each of these is the individual measured number of photons. Some of you might also think right away, well, okay, why do we have to choose to do all of this coherent modulation like we're doing before? Why not modulate the individual number of photons? And if you were thinking that, good on you. That's good intuition. That would be great. Unfortunately, it's very difficult to both tune the individual number of emitted photons as well as detect individual photons up to a specific number. So we can detect the presence of a single photon, but say counting something like 3 photons is difficult. There are some advantages to using this modulation format in certain applications, but we won't talk about this for the rest of the slides. But just know that, yeah, this is in theory possible, has some interesting properties, and this non-coherent photon number modulation, it could definitely be of interest in the future. So an example system might be in the future if you have some quantum dots that are really good emitters that can have a quasi-monochromatic property, and you can choose to emit a certain number of photons and then have a photon number resolving detector. You could have some interesting channels. One thing that's also worth pointing out is that, well, previously I've been showing you the Wigner representation of the coherent states, which look like a blob in the phase space. You can also write a Wigner representation of each of the photon number states. So in this case, photon number 1, 2, 3, and 4. So what you're looking at here is the same phase space representation, but kind of looking at it from an angle and giving it a 3-dimensional property. And what you'll see is that there's these negative values, these associated quasi-probabilities can take negative values in phase space. And so the negativity of the Wigner function is a rough indicator of the quantumness of a state. So that's not to be a totally definitive statement, but generally something that has a Wigner negativity is a quantum state. So we won't talk about this more now, but this is another modulation format that in the future could be relevant. Sorry, and now I will hand it over to Tiju to take it back.
Yes. So somebody had a doubt here, and yeah, let me clarify that not all waves can be splitted like this, but we consider only such waves in this talk. And yeah, that was the main question, I guess. There was one more question in the chat.
Yeah, this one that just came in about explaining the Fock states again. So I'll let you keep sharing, but if you want to hop maybe to the the slide that I have for the coherent state, looks like slide can't tell, 18 maybe.
Yeah.
While he's
So
changing slides, I can explain it again too. But yeah, so the Fock states are a basis. So it's a representation of it's a quantum basis. It's a representation of the field, and that value n corresponds to a discrete number of photons present in the system. So if I gave you an n of 1, it would, in the phase space, it would look like that plot that Tiju was just showing, and it would be that vector 0, 1, 0, 0, 0, 0 on to infinity. A coherent state doesn't just have a set number of photons, it has an average number of photons. And so it's when you write it in the Fock basis, it takes on a superposition across different numbers of photons. We'll see a little bit more about kind of how this plays out, and why this is relevant. But yeah, you can think about it as one of two things. You can either think about it as a basis if you want to think about it in its vector form. It's just this infinite dimensional vector with a single non-zero entry for each n. Or you can think about it as the number of photons measured in that specific situation, or a discrete state with a number of photons. And then I see one other question. I didn't get the concept of Wigner negativity. Could you please briefly go through it again?
perhaps we should.
Yeah, I'll just say briefly. So Wigner states are the Wigner representation is a way to describe the probability, the quasi-probability distribution in phase space. So if I were to measure not individual photon numbers like are listed here, but to measure the operators of either its phase or amplitude, it has, recall, a Heisenberg limited uncertainty. So there's always some probability that you'll measure it at a given range of values, but no discrete value. And that distribution can be plotted out in the way that it's shown there. Yeah, so you can kind of visualize it. The negativity is because this is not a true probability amplitude. It's a quasi-probability amplitude. And the negative value, I think, is a little bit beyond me to give the true intuitive reasoning as to why that's explicitly quantum. But it's a good benchmark to understand the negativity, or whether a state is quantum or not. Hopefully that helps. And sorry, I'll let you take over then, teacher.
Not a problem. Let's move ahead, and I would like to start with this ideal detection of a square pulse. We have seen what is a square pulse from next session, and so I am assuming we are aware of this part, and we are trying, as Jack mentioned, suppose you have a laser light with you and try to measure the number of photons, okay? And you are sending this for a time period t, and let's say we have a photon detector, okay? And if you try to detect us some clicks, let's say, at some discrete points you get some clicks. So you send this laser light, there is a bunch of photons coming in, and at some discrete points you get clicks. That means photon is hitting your photon detector. And then, so the to expand a little bit on the Fock basis which Jack was mentioning, the thing is that a laser light can have any number of photons depending on, so it can have 0 photon, or when you detect, okay, at a particular interval of time, it can give you zero photons, it can give 1 photon, 2 clicks, 3 clicks, it can even give 100 million clicks, okay. But there's a probability associated with which you get these clicks. You may get, according to the mean number of photon, your probability of getting 2 photons is much higher than the probability of getting 100 million photons. So, but there is a non-zero probability. The important fact here is that if you have a square pulse, there's a non-zero probability for getting any number of clicks in a given time period. Okay, so that is why you want to express your mathematical description of your coherent state as an infinite superposition of all the possible number of photons. Okay, so because everything has a non-zero probability, so because of which, that is why it's an infinite dimensional space you have to consider, and it's a superposition of infinite all the possible number of photons you are supposed to get. Okay, so that is what a coherent state is. And as we discussed earlier, uh, this distribution, when you have a square pulse, this distribution follows a Poisson distribution, which is depending on the mean photon number in your square pulse. And to recall, the Poisson distribution is now the parameter is n, which is the mean photon number. It's the probability of obtaining k clicks, or probability of obtaining k number of clicks in your photon detector is e to the power minus n. Let me try to use my laser pointer. Somebody was asking that. Yeah. Probability of k photons is e to the power minus n, which is a constant, times n to the power k divided by k factorial. This is your probability of obtaining k photons. As you can see, this is never zero for any number of k. Even if you take 100 million, 1000 million number k here, there is still a non-zero probability to get that. Okay, that is why you need an infinite dimensional Hilbert space to represent this square pulse. And a basis for that infinite dimensional Hilbert space, which we take, is the number basis or the Fock basis, that is written as ket 0, ket 1, ket 2, etc. And yeah, this derivation we are not giving here, but please take it as a fact for the time being. If you have a square pulse and if you have a photon detector measurement, as I discussed earlier, the measurement is an orthonormal basis of the Hilbert space. If photon detector is the measurement you are choosing, your basis is the Fock basis, 0, ket 1, ket 2, and so on. All right. Now let's look at the coherent state once again. The coherent state alpha is written as, you look at this, alpha is given to you. That means this is a constant. Okay, e to the power minus mod alpha square by 2. This is a constant. And just think of this thing sitting outside the summation, because that doesn't depend on n, right? So you can think of it outside. So after that, it is just summation alpha to the power n divided by square root of n factorial. This is like your exponential function. Okay, we just put a square root of n factorial here to match the probabilities. So it is just alpha summation alpha to the power n divided by square root of n factorial. That is your coherent state. That is the coherent state, and as we discussed, this is the Fock basis. And if you have alpha and beta written like this, you can calculate the scalar product between alpha and beta. This is exponential minus half mod alpha square plus beta square, mod alpha square plus mod beta square, plus alpha star beta. Alpha star is the complex conjugate of alpha. It's okay. So if alpha is a truly complex number, this is mod alpha square and mod beta square. If alpha and beta are real numbers, it is just alpha square and beta square. Okay. In this talk, mostly we'll be dealing with alpha and beta real numbers. That is why it is written like this here. So as we discussed again, probability of observing k photons while measuring alpha in the orthonormal basis or Monoman projective measurement n is the Poisson distribution e to the power minus mod alpha square mod alpha to the power 2k divided by k factorial. And the mean photon number, this is again a back calculation. So the mean photon number is the mean of this distribution. And that turns out to be, if you just do this computation, it turns out to be mod alpha square. Okay, so the mean photon number of a coherent state alpha is mod alpha square. This is something which we want to remember. Okay, so there are two things which we want to remember. The mean photon number is mod alpha square of a coherent state alpha is mod alpha square, and also the probability of getting 0 photons. What is the probability of getting 0 photons here? The probability of getting 0 photons is just putting k is equal to 0 here, right? Uh, and what is the probability of getting non-zero photons? I mean, I'm not saying that k photons you are receiving. I'm saying that you get a non-zero number of clicks. Okay, what is the probability of that? The probability of that should be the 1 minus the probability of getting 0 photons, right? Because total probability is 1. This summation is 1, and the probability of getting 0 photon is this number by putting k is equal to 0, and that is e to the power minus mod alpha square, right? And what is then the probability of getting a non-zero number of clicks? I just want to know whether there was a click or no click. I mean, one click or two click or infinite or 100 clicks doesn't matter for me. I just want to know whether there was a click or a no click. If there was a click, that means the probability is 1 minus the probability of no click. So that is something which we will use later, and keep that in mind. That will be 1 minus e to the power minus mod alpha square, okay? Which is the e to the power minus mod alpha square is the probability of 0 clicks. All right. And let's now look at what is, so equal prior and on-off keying direct detection receiver. Okay, so on-off keying we have seen. On-off keying and equal prior means you are, so now we are trying to send zeros and ones. Let's say we are trying to send zeros and ones using ket 0 and ket alpha. Okay, let's keep this in mind. So classical information means we have already converted our information of message into zeros and ones. Now we want to embed it into a physical system, and let's say we are using coherent states of light for sending your zeros and ones. And suppose our 0 is written as ket 0, and instead of 1 you are sending the coherent state alpha, or the square pulse ket alpha. Now and then these, instead of zeros and ones, these coherent states are moving across your channel, and at the end you want to make a detection, right? Your receiver wants to make a detection of this states, and then decide, based on the detection output, it want to decide which um, alphabet was sent initially, whether it was a 0 or a 1 was sent. So to do that, so we want to make the detection, and then detection here is the direct detection or the photon detection, and then after that we want to make a decision. Okay, so because when you detect, as we discussed earlier, this can have a click or no click. Okay, so based on that we want to decide whether which one was given. So a simple detection rule, or it's called a maximum likelihood detection rule, decision rule, is that after you receive, so to recall, either 0 or alpha is coming. Okay, so you put a detector at the end, and then the detector receives clicks. Okay, and if there was a click, I will say, if there was no click, I will say that 0 was sent, or a coherent state. This is vacuum state, there is nothing here, so it's very unlikely that it will create a click. So we are not counting dark clicks in this setting, so it is an ideal setting. So ket 0 is not supposed to give you any click here, so that's a very perfect decision. If you have 0 click, then you say that, okay, hypothesis 1, that is 0%. If there was 1 click, at least 1 click, okay, that is greater than 0 click, then we say that that comes from alpha. Okay, that is my ML decision rule here. And let's assume that zeros and ones are coming with equal probability for the time being, that is P of H1 or P of H2 is 0. Now, when can we make an error? In this setting, we will make an error when alpha is sent and there was no click. As we discussed earlier, even when alpha is sent, there is a probability of e to the power minus mod alpha square, or e to the power minus n probability that this will not create a click, right? So that is a situation where we make a mistake. So there was, because our decision rule is that if there was no click, we'll say that 0 is sent. So that is a place where we make a mistake. The other way we can make a mistake is 0 is sent and there was a click. So in this setting, we are not assuming that that scenario will happen. So we are assuming that dark clicks won't happen. So that case will not happen for us. So let's look at the derivation. What will be the probability of error? Okay. So yeah, I want to emphasize this fact before we do the computation. The measurement basis. So when you do a measurement, there is a orthonormal basis of your Hilbert space you are choosing. That basis is your Fock basis or the photon number basis. And the decision rule is the ML decision rule. So a measurement basis along with a decision rule is called a receiver. Okay. So a receiver is not just a measurement basis, but after doing the measurement, you want to make a decision. So a measurement basis plus a decision rule is called a receiver. All right. What is the probability of error? The probability of error by definition is the average of the errors you make. Okay, the total probability of error is the average of the errors you make. How are you going to make an error? There are two ways to make an error here, as we discussed earlier. We are given h1, that means 0 was sent, but you decided that h2 was the received one, or alpha was sent, that is h2 was sent, but you decide that h1 was there. This is the scenario I was saying, that alpha was sent, but there was no click recorded in the time which we are measuring. So that means you declared that it was h1. These are the two possible ways in which we make an error. Now, what is the average of these two errors? The average of these two errors is that you have to multiply with the, so this one h1 was sent, right? So what is the probability with which h1 was sent? And here h2 was actually sent. So what is the probability with which h2 was sent? So this product and sum, probability of h1 times probability of h2 given h1 plus probability of h2 times probability of h1 given h2. This is the average probability of error. Let's compute this thing now. More precisely, now the equal prior we have assumed, that is half is the probability of h1 and probability of h2. So let's replace that with p of h1 with half and p of h2 with half here, and then probability of h2 given h1. That means h1 is actually sent, but we don't know. We have decided that h2 was sent. That means this h2 was sent means probability of k greater than 0. Given it was h1, that is one way of error. When there was a vacuum was sent, but we decided that there was h1 was we decided and there were clicks. That is what this error. And then h2 was sent, but there was no click recorded. That is the probability of k is equal to 0 given h2. Now let's go to the poll question. Jack, could you please launch this poll?
Yeah, trying. One sec. There we go.
Okay. What is probability of k greater than 0 given h1? You may look at the screen. Give h1 is your vacuum state. When the vacuum state is given, what is the probability of getting a positive number of clicks? As I discussed earlier, this was a scenario where it's a perfect situation. We don't have dark clicks.
Sorry, Tiju, you're muted.
Oh, I'm sorry. I'm sorry. Yeah, yeah, yeah. So I have entered the poll and let's see the results. Uh, so this was about 32% got it correct, but I think there was a confusion in this because let's think that H1 was given to you, right? H1 means your actually sent state is vacuum state. Okay, vacuum state means it is n is equal to 0, right? So if n is equal to 0, we are not supposed to get any clicks. That's what I was saying, that we are not assuming that there will be dark clicks. So this a vacuum state, there is no click. So the right answer is A. Okay. Now I'd like to do one more poll. That is just the next. Oh, sorry. Next poll is, what is the probability of k is equal to 0 when H2 is given? So here, look at it carefully. It is H2 is given. That means your coherent state alpha is being sent. What is the probability that you won't get a click? Okay, about 52% people have participated. Let's end the poll. All right, this time most people got it right. So the probability of k is equal to 0 given H2 is the probability of getting 0 clicks when alpha is given sent, right? Get alpha is sent, and that is e to the power minus n, which is e to the power minus mod alpha square. Very good, thanks a lot. And let's move ahead. Okay, let's continue with our computation of probability of error. Probability of error is probability of this computation we were doing, and we in the poll we were actually calculating this term, and with the answers which is already known now. This term, when you are sending once this, the people had some confusion here, I guess. So let me tell you once again that if you send a coherent state, that means n is equal to 0. Okay, in that case we don't get a click. So that is why this is 0. The probability of getting a positive number of click is 0. And if you're sending H2, but there is still a chance of getting a 0 click with a probability e to the power minus n, and therefore probability of k is equal to 0 when H2 is given is e to the power minus n. Therefore, the probability of error for this on-off keying with the direct detection receiver is half of e to the power minus n, which is this term. All right, so we have seen this on-off keying and direct detection receiver. Now, where are we now? We were looking at this setting initially. We want to send a message. Different modulation formats are there, and coherent state 0 and alpha, that is the on-off keying that we discussed, and the modulation format, that's the modulation format, and direct detection, that is photon number basis plus the maximum likelihood decision rule as the receiver mechanism to send and receive a single bit of information. We also derived a probability of error for this system. So next, we will discuss about the minimum probability of error that is inherent in the system while detecting two general pure states using an arbitrary orthonormal basis. So what happens here is that, as we discussed, this is a quantum system we are dealing with. So it is not possible to perfectly distinguish two quantum states. There will always be some probability of error. Okay, so we will now discuss what is that minimum probability of error that is inherent in the system, and how to build a receiver which can minimize that, which can achieve that minimum probability. So what is that's supposed to be an ideal receiver, right? That we know that given two quantum states, there is going to be some kind of an error you are bound to make. Okay, because these systems are quantum, this is not deterministic. But then how to build a receiver that will minimize the error? Okay, so this is what we are going to do next. Let's look at it in a more abstract way. Let's assume that you have two states, C1 and C2 given to you. Even though in our setting, the C1 and C2 are infinite dimensional states, if you are given only two states, you can actually generate a two-dimensional vector space using those two states, right? So therefore, we just need to look at only these two plane and C1 and C2 as the vectors. And let's assume that we have our basis, okay, the monoman basis or monoman projection basis, that is a orthonormal basis written as omega 1 and omega 2. And don't worry about all these thetas and phi. Just think that phi indicates the angle with which omega 1 makes with the real axis, and theta is the states which you want to uh, distinguish. Okay, so the angle with which the C1 makes to the real axis. And also we are making an extra assumption here that the states which we are sending, let's say C1 and C2, they are both equidistant from equiangular from the real axis. Okay, that means both C1 and C2 makes an angle theta with the real line. So we can always do this, right? Because if you are taking two vectors and then you can just put a line through the middle of this angle. You can split that angle between these two vectors equally and write a straight line, draw a straight line between them, so that that becomes your x-axis. Okay, so you can always place your given states C1 and C2 like that. That's why we are able to assume this angular separation between these C1 and C2 with the real line. Now our goal, okay, this is important for us. The important fact is that how to place this omega 1 and omega 2. What is the ideal location or ideal placement of omega 1 and omega 2 so that you will minimize your probability of error? That's what we are going to do. Is the goal clear to everybody? The goal is to place omega 1 and omega 2, which is our measurement basis, in such a way that we minimize the error. Okay, that's what we are trying to do here. Now, let's look at probability of the error. Okay, the probability of assuming getting 1 given 2. Okay, so probability of 1 given 2, if you are measuring in the basis omega 1 omega 2, measuring C1 and C2, you are actually sending C2 and you are declaring omega 1. Let's say, what is the probability of 1 given 2? That is this number. This is something which we discussed in the initial few slides. The probability if you're measuring in the basis omega 1 and omega 2, some given vector C2, the probability of getting omega 1 or the output 1 is absolute value of scalar product omega 1 C to the whole square. That is coming from basic quantum mechanics, and that can be computed as cos square theta plus phi. Similarly, probability of getting the output 2 given C1, that is scalar, the absolute value of the scalar product of omega 2 with C1, absolute value of square, that can become sine square theta minus phi. Don't worry about these descriptions, these sines and causes at this point. It is just that we are using this formula. Okay, now the probability of error by definition is that prior probability of 1 multiplied with the probability of 2 given 1, and prior probability of 2 multiplied with that is 1 minus p multiplied with probability of 1 given 2. That is the probability of error. Now look at this. Probability of error is a function of phi. We want to adjust phi, right? We want to adjust omega 1 and omega 2. We want to place omega 1 and omega 2 in such a way that we minimize the error. So we consider this probability of error as a function of this phi and differentiate with respect to that. Okay, so to minimize the probability of error, we differentiate probability of error, the formula which we get for probability of error with respect to phi, uh, uh, and put it to 0, and that gives a relationship between phi and theta that follows tan 2 theta is this is a computation which I am leaving for you. And then as an exercise, what you can show is that then you minimize this function. Okay, this minimizing this function, you see that probability, the minimum probability of error inherent in the system is half of 1 minus square root of 1 minus 4p times 1 minus p times sigma square, where sigma is cos 2 theta. Okay, the scalar product between C1 and C2. This is interesting. One interesting thing which you should notice here is that this depends only on p and sigma. Okay, so that means the minimum probability of error in this setting. So we have this setting here. We have a C1 and C2 are given to you, and there is some prior probability with which we are sending C1 and C2. And when we try to measure the probability of error, if you try to minimize the probability of error, the minimum probability of error depends only on this theta, that is cos 2 theta will be the sigma, and the prior. Okay, so nothing else. That is the minimum probability of error. And if you further take equal priors, that was what we took when we discussed on-off keying. And if you take, we will see more examples with the equal priors. If you take equal, so that means if the probability p is known to be half, and then it just depends only on the sigma square. Okay, so once you know the prior probabilities for C1 and C2, the minimum probability of error depends only on theta. This is something which you have to remember in this talk. Only on the angle between these two vectors we are choosing. That is that is the only parameter or only variable for the probability of error. All right. Now, one more thing which we can notice here is that since this depends, this depends only on sigma, and sigma is scalar product C1 and C2. If you apply unitary operation to both C1 and C2, let's say you have instead of C1 and C2, you are having some unitary transformations here, which U is the unitary transformation which transforms C1 as U C1 and C2 as U C2, then still this number is not changing, right? So this probability of error does not change under unitary transformation. So unitary transformation uh, does not change the distinguishability of two states. All right, that is something which we have to keep in mind, because these are the kind of pre-processing, pre-measurement things which we can do. So we can do some unitary transformations to place things properly without changing the distinguishability. Now let's look at BPSK coherent state discrimination. BPSK means you are given alpha and minus alpha. That is binary phase shift keying. You are having two coherent states now, alpha and minus alpha. And then this is the sigma. The sigma here is that alpha and minus are the scalar product between the coherent state alpha and the coherent state minus alpha. That is e to the power minus 2n. If you look at the definitions, you will get it easily. And this is just a pictorial representation of the same. And minimum probability of error, if you have equal priors, it is just half of 1 minus square root of 1 minus sigma square. As we know, the sigma is this thing, sigma square is e to the power minus 4n. Therefore, probability of error, minimum probability of error for the BPSK coherent state discrimination is this number, okay, half of 1 minus square root of 1 minus e to the power minus 4n. And now we discuss a hypothetical receiver which can achieve this probability of error. So let's take alpha and minus alpha and PPSK modulation, and then try to, and there is a design of a receiver which was done by Sam Dolinar in 1978, which achieves this minimum probability of error. Okay, we are not going to derive this receiver, but we'll just state that Dolnar receiver is a receiver design which achieves this minimum probability of error. Such a thing, hypothetical receiver exists. So the point is to build receivers which can go closer and closer to this minimum probability of error. So one thing to notice here is that it was very easy to compute the minimum probability of error. It is just basic calculus to compute the minimum probability of error. But to actually make a receiver that can achieve the minimum probability of error, that's a non-trivial task. And that is why we are not discussing that in this small mini course we have here. So this kind of a phenomena is seen in throughout quantum theory or quantum information. Theoretical bounds can be obtained fairly easy way, but to build things which achieve that bound is really hard often. Okay. Once again, where are we now? Well, we are trying to send and receive information, and we learned there are some inherent errors. Therefore, that means there's a probability of error. In the case of on-off keying, we looked at the modulation format on-off keying, that is 0 and alpha, and then direct detection as your receiver design. That means photon number basis and ML decision rule. Then we derived our minimum probability of error inherent in a one-domain measurement plus maximum likelihood detection receiver for general pure states. And also we looked at we gave a flavor of what is the Dolinar receiver, which achieves the minimum probability of error. Okay. The next is what is known as Homodyne detection. That is a very ubiquitous detection method in optical labs, and we will look at the Homodyne detection for BPSK symbols. Before that, let's look at this direct detection, which we were discussing once again. We are sending a square pulse, we are getting at discrete time intervals, we are getting some clicks. And let's say we are applying some gain to this photocurrent we get, and then integrate it throughout the time period you have, and then you get a actual random variable. So here you get only a discrete set of clicks, and you apply some gain, and then you integrate throughout, you get a random variable y. And this y, when n is very large, when your n is very large, we know that this is a Poisson distribution, we know always. And when n is very large, this Poisson can be approximated using a Gaussian distribution with mean, mu, and sigma square. And if you apply this gain and this integration, if you do, then your mean mu will be q g, the gain, and this number, this constant s times your n, and sigma square will be just the square of this guy with n. Okay. And this is going to be your mean and covariance for the ideal direct detection. And we use this fact to do the Homodyne detection. Okay, the Homodyne detection, what happens is that we are sending this alpha, so we want to detect alpha. Okay, the basic idea is that what we do is that we mix this alpha with a very large local oscillator. Okay, this thing is under our control. We'll send one more wave, which we call as local oscillator or LO, alpha LO. We send one more coherent state and mix these two things together. Okay, and then at the output we mix these two things, and you get these kind of alpha plus alpha LO divided by square root of 2 and alpha minus alpha LO divided by square root of 2. And we do the same photon detection at each arm. So there are two arms here. This is the unknown alpha we are receiving, and this is under our control. We are mixing that with a strong local oscillator, and we separately get these two outputs. We make the measurements and do the same thing what we did earlier, the gain and the integrated over the time, to get a random variable output. And once you get that output, for when you have very large local oscillator, we can approximate these posons. We have one poson here and another poson here, and these posons with a normal distribution, and with n plus being this modulus and n minus being that modulus square. So in the Homodyne detection setting, if you do this thing, at the end what you're going to get is a normal distribution y here, okay, at the output, and it has a specific mean and covariance, mean and variance. All right. And here the point is that we can choose our alpha LO and our G and S. Okay, our scaling constant S, we can choose that in such a way that this output distribution has a mean alpha. So alpha was the original one sent. That is how we are going to detect that at the end of the detection, we are going to decide that alpha was being sent. Okay, so we can choose your S appropriately in such a way that this Y will follow a normal distribution with mean alpha and variance 1 over alpha. That it follows from this computation we can do here, and we don't do the computation here, but this is left as an exercise. And 1 by 4, this number 1 by 4 is known as the short noise limit. All right, and all this thing with the this mixing, this equal mixing, kind of equal mixing, this is called a balanced detector. And how to do detection or discriminate alpha and minus alpha using a Homodyne detector. Okay, so we have alpha, and let's choose some alpha LO. Okay, that means we are choosing another coherent state, which is another angle theta, so that at the end we are going to get a normal distribution with real part of alpha times e to the power I theta LO and 1 over 4 as your this is your mean, and 1 over 4 as the variance. And we need now a decision rule, right? So we get some probability distribution at the output. After doing all this stuff, we get a probability distribution at the output, and that probability distribution, suppose you say you are sending alpha or minus alpha. Okay, now we want to distinguish between them, so that means we need a decision rule. Okay, so let's when you send alpha, as we discussed earlier, you get a normal distribution centered at alpha, right? That is a normal distribution like this is what you are going to get. And when you send minus alpha, we get a normal distribution centered at minus alpha. Okay, so we want, so the output is either this one or this one. Okay, from the obtained value or the measured value, we want to make a decision whether it was alpha sent or a minus alpha was sent. Okay, so the decision rule is the ML decision rule, maximum likelihood decision rule. What we do here is, for when y is greater than 0, the observed value or the measured value of y, if it is a positive number, that means that lies here. Okay, so you can see that it's natural to think that if the value is here, it's a very high probability that that was coming from alpha. Okay, or if you have y is negative, that means the y falls here on this part. Okay, the observed value of y falls at this part, then it's a very high probability that it comes from minus alpha. So we say it is minus alpha. That is the ML decision rule for homodyne detection. But as you can see, if even when your minus alpha was sent, there is some probability with which it can still be positive, right? That is this part. Okay, therefore there's a possibility of error at this part. And also, even when alpha was sent, there's some probability with which it can take a negative value, that is here, this probability. So we can make errors here also, here as well. So there's a probability of error in this place. The same computation of probability of error will give you this probability of error is half this function. Okay, this can be that is just this integration. Okay, integration of the from this part to this part for the positive, and from this part to this part. That is the error function we have, and the probability of error is given by this expression here. All right, now let's move to Jack's session where we do some some
Yeah. So I'm going to hop in here. We'll keep I'll switch over to my screen quickly. It's going to look the same as what Tiju is sharing. Let's see. Should be able to see it. Let me put on annotate. Okay. So here's what we're going to do. We are going to we're going to go ahead and we're going to open up a Google Colab. That's going to allow us to kind of do some quick checks of our knowledge and get our feet wet with using some numerical modeling for systems like this. So we'll do a little bit right now. We're going to come back to this again later once we have our understanding of the final part of the class. So here's what's going to happen. In general, we're going to go to colab.google.com and we're going to open a Colab from the top bar. We'll select GitHub, and then really I'm going to post in the chat here in a second that all we need to do is type in my name here /winter school, and it's going to pull up the ability to just load into this notebook. So I'm going to walk through it kind of step by step, and then we'll pause, and I'll probably do it one more time just to make sure that we're all getting there. And then we'll go through just a few cells. Oh, I think my screen is now sharing. It was probably delayed before.
Jack, can you post the links in the chat for all of our attendees? Thank you.
That now. So I'll walk through it, but what you're going to do is copy what I'm typing right here. Okay. And we're going to go to colab.google.com. So let me do this in my browser as well. So let's see. Hopefully you guys, can you see my browser right now? Hopefully Tiju or Brianna, can you see it?
Yes, we can see.
Okay, cool. Yeah, so colab.google. I guess you don't even need .com. Interesting. And at the top, you'll see this toolbar where you can hit Open Colab or New Notebook. Go ahead and click Open Colab. And then you'll get this selection window that will pop up for you to choose one. On the left-hand side, there's an option for GitHub. Go ahead and click on that. And then it's going to allow you to enter a URL or search by an organization or user. And that's where you will take what I posted in the chat. So my name /winter school. And then if you hit enter, it will pull up a repository with a branch. And then below that, you'll see info in Photon examples.ipy notebook. That's when we're going to click. So Click on that and it should open. I'm going to go through that one more time, just in case anyone got lost along the way. So step one, open up a web browser and go to colab.google. And it should look like this on the home page. Just Google's Colab. At the top right, you'll see a few options. There's Open Colab, New Notebook, and Sign Up. All you need to do is click Open Colab. And there's going to be a selection window for you. Don't click New Notebook or cancel or anything. Go to the left-hand side of that pop-up. Choose GitHub. And then I posted this in the chat, or you can just type it. But you'll do Jack Postlethwaite / winter school search, and it's going to pull up this example, info in Photon examples. Okay. Let's do this. I'm going to continue on now. I'm going to start by running this first cell because it takes a minute. Yep, run anyways. So this is going to import all of the necessary packages. And while that's happening, I'll talk through. So what we're going to do is we're going to go through a few cells. You guys should also start by running this first one because it takes a minute to just get all the packages. And if you are stuck right now, I think we'll take a short break throughout this once we've kind of run through it. So you can post your questions in here and I'll try and help people through it. Yeah, we're gonna kind of walk through some examples right now. So this first one takes about 30 seconds, I think. Okay. So the first one is run. Okay, so now if you scroll down a little bit further into the notebook, you'll see section 1 starts here. And below that, we're going to start with the simplest thing we can do right now, just to get our feet wet with Python. We're going to model a Poisson point process. So this is similar to what we're talking about when we've said that photo detection of a coherent state is a Poisson process. So when it's a weak state, like in this case, we're choosing a mean value of 0.5, or I guess I put 1 here. You can choose whatever value you want. So choose a mean value and then generate samples. I'm not sure, actually, we don't need so many. So if you're running it and it's taking a while, you can reduce the number of samples by looking at this line that says samples equals NP random Poisson, and just change that number down to something like maybe 1,000. And below that, we're just going to plot it. So we just want to make sure that we understand what a Poisson point process is. So in this case, I did like 10,000. I just did 1,000 samples. And I'm just binning it right now so that way we see that we have this high likelihood of generating 1 click. And that makes sense because that's our mean. But we have some tail probabilities of generating things as high as like 5 photons. So this would be the detection statistics you would get if you had a weak coherent state that was incident on an ideal photodetector. So this means that all of the light is totally coming in, hitting the photon detector, but you have a kind of a weak coherent state. And as a ballpark, if you take like a regular laser pointer of like, a few milliwatts and shine it at a photodetector, not your eye, at a photodetector, you would get, I guess it depends on how far away you are, but something like, billions of photons. So it would be way, way higher. So we're talking about really, really weak light here. And this is relevant in the case of like deep space communications. Okay. So all we've done so far is we've just modeled just a Poisson point process. But now let's do something a little bit more. So we're going to kind of look at the statistics of Homodyne, which is what TG was just showing us before. So again, I might reduce the number of samples by a bit here. But what I'm going to do is I'm going to choose 2 different mean values, one with an amplitude of 1, one with -1, and then we're just going to plot these. And we should see a plot in a second with a line down the middle. So great. So, this plot with only using 1,000 samples on each one, you can start to see the Gaussian curve coming out, but it's quite a bit noisy, right? So, and you can even see that there are some crossover probabilities. Maybe it's easier to see the orange on the right side here. So this is the type of thing that would happen if whenever we're doing our detection with Homodyne, we choose to always just have our maximum likelihood decision rule. If I have a positive value, I will decode that as the positive, we'll call it H1, a negative value is H2. And in this case, we would have had an error. So there's some likelihood. And if I increase it, we'll make it just a few more samples. We'll start to see that it's going to look more and more clean as a Gaussian. But the overall number of errors on average, the relative rate of error will remain the same since we haven't changed our mean or variance. So I guess, yeah, you can't really see the blue ones here because it looks like they're occluded by the orange statistics. But yeah, you can see clearly that there are some error statistics here. Okay, so for those of you that haven't seen Python, maybe this is nice. You've just seen how to just model statistic. So be it a Poisson or normal distribution with the NumPy functions. But what we actually want to do here is start to look at modeling optical systems because that's what's relevant to us. So the next step here is we're going to use a package called Strawberry Fields. So this is a package from Xanadu. They're a photonic quantum computing company based in Canada. They developed this really nice Python package called Strawberry Fields, which is basically a great calculator for photonic systems. In their package, you have a few different options. You can choose how many modes you want to model. So in this case, we're going to say that our program is just going to model one optical mode. So this is a lot like what we've been talking about the whole time. There's just one field, and we want to model it. The engine we're going to choose here is the Gaussian option. So this is not something that's going to be talked about in this course. I believe it's maybe touched on in some of the others. But the Gaussian package is an efficient way to model optical systems that have some classical properties or quasi-classical, as well as a few, just we'll say quasi-classical. But basically, instead of modeling all of the Fock vectors, like I said before, is really difficult because it's an infinite dimensional space. We're going to compress this down and we're just going to record things like the mean and the variance as a way to simplify the representation because we can pull out all the properties just based on those values. So here we have our Gaussian backend, and we're going to choose to represent a state alpha, which we're pulling from earlier in the code. And we're going to say, let's start this circuit. So our circuit is going to be called Q. And in the 0th mode, we're going to put a coherent state with a complex amplitude alpha. All we're going to do then is we're going to take that same mode, Q0, and we're going to measure Homodyne on it. So this is already a built-in function from Strawberry Fields. It's not something that you have to build from scratch. You can just use it and you just tell it which mode you want to act on, and then we're going to run this. So our result is the output of this program, and we just want to return the samples, so the value collected from that 0th mode measurement. So we'll define the system. I don't know if that actually ran or not. Yep, it looks like it did. Okay, and then we're going to run it a bunch of times below. So now we're going to run the system. We're going to run this BPSK sample Homodyne, and each time we're going to collect a sample, and we'll see what it looks like if we run it 10,000 times. So this might take a second. We'll see. Taking a few seconds. Boy, okay, took a while. All right. Hey, look at that. We have a sample of 10,000 samples of the system, and we can see clearly that the coherent state we were looking at, alpha, had a mean value of 2 here. So this makes sense. We get a Gaussian distribution. We see that there are some negative values. So, if we had 2 of these, these would probably be our error results if we were sampling it. And to see that a little bit more clearly, let's do that. Let's actually take Strawberry Fields again. And this time, instead of having 1 mode, we're going to make it 2, so we can see 2 of them. We'll again use the Gaussian backend. And we're going to put alpha in Q0 and minus alpha in Q1. So below that, these are all just going to be plotting. We'll also look at the state in mode 0. So I think we're going to get a Wigner plot here. So let's go ahead and just run this next cell. Hey, look at that. Awesome. So we're seeing now these probability distributions in Wigner space of each of these coherent states. So this would be like coherent states 1 or alpha and minus alpha, and then the phase space. Now, an important distinction that we won't go through here in too much detail is that if you look at this Wigner plot is showing the center value of 2, just like our distribution did above, even though I put an alpha of 1 here. Don't get too caught up on this, but it actually just comes from the definition of the Wigner function and the choice of H or H bar in the background of this. So Strawberry Fields chooses the default H bar, I believe, of 1 here, or sorry, no, yeah, of 2. And so that's going to push this over here. So you do have to be careful. In general, when you're modeling these systems, a lot of times there will be a default choice for the Planck constant, and that will shift you by a factor of 2 or root 2, depending on your choice. So just be careful of that, but the statistics are going to be the same for us. So yeah, so we've now been able to visualize those states, and you can imagine the projection of them for Homodyne would again generate to you this Gaussian curve, just like you saw before. Okay, and then the last thing we're going to do in this section, just to do some more visualization, is visualize those Fock states, similar to what I showed in the slides earlier. So this is going to use a single mode for Strawberry Fields, but instead of using the Gaussian backend, we're going to use the Fock backend. And we are going to have to also define the cutoff. So remember, because the Fock representation is an infinite dimensional Hilbert space, we're not going to be able to represent it efficiently in a computer. So we're going to choose a cutoff. And in this case, we're going to choose to define the cutoff space to just be one more than the whatever the value of n we're going to look at is. So it's an efficient representation. We're just going to put one photon using this Fock function into the 0th mode, and we're going to run it, and we're going to plot it. So we'll run this definition, and then in the cell right below hand, we'll visualize a Fock state. And in this case, it is the 4 Fock state. So you can see the negativity of this, making this Wigner negativity that's indicative of a quantum state. And this is just the heat map representation. And feel free to play around with this. If you make this number really big, your computer or the collab might not be happy, but like we can change this to just represent the 3 Fock state, and we'll see it run through and generate the Wigner function. So they're kind of aesthetically pleasing, I think, to look at, but it's interesting to see these dips, these ridges and dips for the Fock states. Okay, and what we've seen so far is the ability to use Strawberry Fields to model these photonic systems and give us nice visualizations. So that's the end of the first section here. We will come back to this later to do some more for studying the actual properties of the channel. And for now, Tiju, what do you say we take a short break here before we come back? And then if people have questions, they can throw them in the chat now. I think we'll do that. We'll take a
Yeah, 5 minutes break. Yeah.
Yeah, take a 5-minute break. So we'll be back at 51 minutes after the hour, roughly. Yeah. All right. I'm going to stop sharing. Post some questions if you have them. We'll be back in just a minute and we can answer those.
Great.
Actually, I'll just pause the screen. Okay. Not going to call an end to the break yet. I'm sure people are kind of still getting back, but while that's happening, let's maybe discuss a few of there's two questions I see right now. And so we'll kind of start with the one of them that's related to troubleshooting the code. So if any of you are not seeing the Wigner negativity, which you should be seeing in this Fox state run at the end, I would say make sure that you aren't choosing 0 for nval, first of all. If you choose 0 for the visualize Fox state, what that's going to give you is the vacuum. Sorry, I wasn't sharing my screen. There, we'll share it again. So if you aren't seeing this negativity in the visualize Fox state, yeah, first thing to check is make sure that you didn't put 0 in here. If you put 0, you're going to see the vacuum state, which is true that it is, yes, the 0 photon, but it's also the vacuum state Gaussian. So that one will be, it won't have any negativity. Otherwise, I would say just make sure that your line, things, I guess, as you're tabbing through, things can change sometimes. But if you look at this, the main thing I would say is make sure that you're initializing a Fox state with this program context. If that somehow got changed to something else, then you might not be seeing the negativity. In addition, I would just say make sure that whatever you see at the bottom where it says result, for mine, it says result equals eng.run program. Make sure that that same value is the one that you're using to grab things later. So like here, when we're getting the values of the Wigner function, we're saying y is equal to result.state.Wigner. So just make sure that that's not something else like results plural or something like that. And again, below state equals result.state. If those things are true, if your code looks like this, it should be generating the Wigner negativity, and you should see a Fox state that looks like this. If not, then I think this leads into the next question pretty well, which was really just about, sorry, I have something on here. There we go. Documentation for Strawberry Fields. So Strawberry Fields is pretty well documented in their website. So if you go to Google, you can type Strawberry Fields Xanadu. I think usually if you type Strawberry Fields, it might give you like the Beatles song and stuff. But um, yeah, so Strawberry Fields, search like Xanadu Strawberry Fields, and I'll just do it. So Xanadu Strawberry Fields, and you'll see it pop up. Yeah, it's this first one. So they have pretty good documentation on most things. One of the things I would say you can do is if you go to like learn and you go to tutorials, they have all sorts of ones that kind of start out with the basics of making up different circuits and doing measurements in there. So we've done really just a basic one so far. They have all sorts of cool demonstrations here. And you can build up into bigger, more complex like quantum algorithms. And really keep in mind that Strawberry Fields is like the calculator for Xanadu. And they even go beyond this quite a bit if you're willing to go over to Penny Lane, which is the other main documentation or their other main like language for quantum modeling. And that one's more about general quantum computation and AI specifically. But Strawberry Fields is like the photonic backend calculator. So it's pretty useful. And the question specifically was about how does the Homodyne measurement work? So like if I go back to the example here, um, let's see, up here. So I said I want to measure Homodyne, and I passed this value of 0. And so you might be saying like, well, what is that 0? Like, why does that matter? Um, what it really is it's choosing it's like changing the local oscillator in the description that Tiju gave us. So if you choose 0, you're choosing to project along that x-axis. And so if I look at Strawberry Fields documentation, like this phi of 0 is the same as choosing measure x. So this is another way we could have done it. Or if you choose to pass it a value, an angle of pi over 2, imagine that you're projecting along that y-axis line. And so, yeah, the way that they do it in the back end is a little bit more complicated than what we're going to talk about here. But in their Gaussian backend, they're using a finitely squeezed state to model an effective projection. So we won't go into that. But yeah, what you're really choosing is you're choosing that local oscillator, and you can imagine it as choosing the line of which you're going to project your states onto. So if I look visually at my coherent state here, imagine that, I wonder if I can actually just draw. So let's draw a straight line. So like, let's say right at 0 here, there's a line, and here is 0. Okay, so like, see, I have a coherent state here. And this is the 0, 0 point, so this would be the vacuum. When I choose a value of 0 to pass into Homodyne, what it's really saying is like project along this axis. And that's the equivalent to the description that we showed before with the local oscillator being in phase to our state. You could choose to also project along this line. But imagine, if I put phi over 2 and I project along that axis, imagine I have BPSK. So I have one coherent state centered here and another centered over here. What you would see is that the projection would be the same for both of them. They would both be Gaussian centered at 0 because both of them have a complex amplitude of 0 or a complex, their complex component, their imaginary component is 0. They're both real in this case. How do I go back to laser? Okay. And how do I get rid of that? There we go. So, yeah, and then when you see the projection, it's like these were the results, like it was centered at 2 here, right? So like this was the projection onto that x-axis line. Yeah, so Strawberry Fields, pretty good documentation. You can just find it by clicking the documentation tab. On the side here, they have all sorts of things. Let me close that. Operations, so sf.ops is the one that carries most of the things you're going to want to see. So you have things like displacement gates and rotation gates, etc. And there's a lot. I mean, like this could be a whole thing all on its own. And Xanadu has some YouTube videos that are helpful, but the tutorials, I think, just from their quantum photonics tutorials are quite helpful. So we're going to come back to this and see a little bit more how to use Strawberry Fields and just numerical modeling here, but it's a cool tool to learn about. So with that, I think we've answered all the questions here, so we can hop back into the slides. So I'll let Tiju take over.
I hope the slides are visible.
They are not for me right now.
Can you click on my window? It's
Oh, yep. Yep.
It's there, right?
Yes, it's
All
there.
right. Where are we now? The same setting of information transmission. First, we learned the probability of error with coherent state. This on-off keying, this coherent state 0 and alpha as the medium and direct detection, photon number basis plus ML decision rule as the receiver design to send and receive a single bit of information. Secondly, we derived what is the minimum probability of error inherent in a one-on-one measurement plus maximum likelihood detection receiver of two general pure states. And then we looked at a receiver design by Sam's Dolinar, which achieved minimum probability of error for BPSK symbols. Another one was the Homodyne detection for discrete BPSK symbol as a receiver design. And then Jack walked you through certain codes that help us visualize and compare what we have learned. And what we are going to do in the second half of this talk is we are going to see the entire thing, the whole this part, okay, including the noise. The whole this part is a communication channel, and as described by Cloud Shannon. And then we try to compare the capacities, channel capacities of each of these designs. First, we need to learn a few things before we really go into channels. That is just what is a transition probability matrix. So the information channel. So this Shannon's information channel is just a probability it's a probability y given x. Okay, so you are sending x, which is known as the source symbol, and at the end you are guessing y as the random variable, which tries to approximate x. Okay, in the sense that y is what we measure and decide as the output, we get as output, and then from there we have to make sense of x. Then, so an example of, let's say x is just 1, 2, this set 1, 2, and y is 2, 3. You are sending 1 and 2, let's say, and receiving 1, 2, or 3. And let's say you have a probability for sending 1 and receiving 1, and sending 1 and receiving 2, or sending 1 and receiving 3. Similarly, sending 2 and receiving 1, 2, or 3. This is called a transition probability matrix. Probability of y given x, such as some j is given, sent, but I is received. P of y given x, I comma j, or x, y comma xp, right? That's called a transition probability matrix. And this is a doubly stochastic matrix. That means that if you sum this row, you will get 1. That is a property of a conditional probability distribution. And similarly, we sum over the columns, that is also 1. That is known as a doubly stochastic matrix. Mathematically, this is because of the properties of conditional probability distributions. Okay, and abstractly, an information channel or Shannon information channel is just a conditional probability distribution given like this, which can be, in the discrete case, this can be expressed using a transition probability matrix. All right. Now, one of the most basic example of a transition or of a channel is the binary symmetric channel. Okay. In the binary symmetric channel, what happens is that, let's say you have same number of inputs and same number of outputs. That is there. And then suppose you send the received y is 1 or 2 with a probability 1 minus p or p. Okay. One is sent, and it can be flipped to 2 with a probability p. It is essentially that. If 2 is sent, that can be flipped to 1 with a probability p. So that is the binary symmetric channel. Okay. So just notice that if p is equal to half, that means with equal probability, this 1 can be flipped to 2, or 1 can be flipped to 1 can stay same. Okay. That is just sending 1 and tossing a coin and see the output, and that is your what is the if the coin is falls as head, let's say it's 1 itself, or coin falls as tail, you say it is 2. So in this way, we cannot get any idea what was sent, right? So that is why p is equal to half is not useful for the binary symmetric channel. If p is not half, then definitely we can have more information. So this idea that p is equal to half is not giving you any useful information from the channel is going to play a role later. So to conclude, a binary symmetric channel flips the output, okay, flips the input with a probability p. If 1 is sent with a probability p, it can become 2, or with probability 1 minus p, it remains the same. For the 2 also, it is the same. So the transition probability matrix, p of 1 given 1, that is 1 minus p, p of 2 given 1, okay, p of 2 given 1, that is p, and now p of 1 given 2, p of 1 given 2, that is p, and p of 2 given 2 is 1 minus p. That is how the transition probability matrix of a binary symmetric channel looks like. And the question is, how many bits can be sent reliably per channel? Let's look at it in terms of our BPSK symbols, BPSK modulation, and direct detection receiver. Okay, modulation, sorry, and the Dolinar receiver. Yeah, BPSK and Dolinar. In this setting, we have this BPSK symbols, that is alpha and minus alpha are our symbols which we are sending. Let's write it as 1 and 2. This goes through our channel, okay, let's say, and at the output we have 1 or 2, okay, and alpha, that is again alpha or minus alpha. This is what the setting is. Because if you remember in the BPSK with digit detection or the Dolinar receiver, which we did not completely explain, the output remains the same as the input. There are no new outputs. In general, for a channel, the output need not be the same as the inputs, okay? But for the BPSK with direct detection or the Dolinar receiver, the outputs are also the same thing, but there's probability with which it will flip, right? Like the probability of error we had earlier, right? The probability of error is PE with respect to this probability. 1 can be flipped to 2, or 2 can be flipped to 1. That is what the probability of error is. And that is the reason why BPSK plus Dolinar becomes a binary symmetric channel. And in this case, the TPM, the transition probability matrix, as we discussed earlier, the same. But for any binary symmetric channel, the TPM looks like this. Let me use the laser pointer. Yeah. for any binary symmetric channel, the TPM looks like this. And since the BPSK plus Dolinar is a binary symmetric channel, we get the transition probability metrics like this. Now, our next channel is BPSK modulation again, but this time we use Homodyne receiver. Yeah. Understand that the modulation alone does not induce a channel. The modulation plus the receiver, okay, all these things together will make a channel. So previously this channel was BPSK with the Dominar, and we saw the TPM transition probability metrics. And now if you have a modulation BPSK with Homodyne receiver, still if you recall, still our outputs are just alpha or minus alpha, and there is a probability of error with which one can be flipped to 2 or 2 can be flipped to 1, and hence BPSK modulation and Homodyne receiver is still a binary symmetric channel. They induce a binary symmetric channel, and the transition probability metrics will look like again the same, but this time the P is different. The P is the error function we got in the Homodyne receiver. So previously in the BPSK plus Dolinar, the error function was this this P. This is the minimum probability of error. And for the Homodyne receiver, that's another error. But the channel, the structure of the channel is same. This is a binary symmetric channel. All right, now let's look at a few theoretical concepts which are required to define what is the capacity of the channel, and we will see the capacities of the channels induced by various modulation and receiver formats we have used in this, we have described in this mini course. To discuss that, we need to understand the basic concept, a basic concept known as entropy of a random variable. Okay, so you are given a random variable. Let's say it's a binary random variable. That means x takes value 1 or 2, just two numbers only. Let's say that our random variable x takes, and px1 is equal to p and px2 is equal to 1 minus p. Let's say just like our you know, these channels which we are looking at. Okay, these random variables are taking at the end, that's taking only two values. Okay, and to the first value with a probability p and second value with a probability 1 minus p. Let's say that is the case. The entropy of such a random variable, that's written as h of x, is written as minus p log p minus 1 minus p log 1 minus p. So this, as a function of p, you can see that this takes this kind of a curve. Okay, so as p moves here, the value of h2 of p or h of x, okay, this if you just plot against p, you will get like that. And as at p is equal to half, you can see that entropy is 1. Okay, so that is again related to what I was saying, that if in a binary symmetric channel, if p is equal to half, we cannot get useful information. That's related to that, not exactly that. Okay, yeah, anyway. Now let's say that we have x takes value over the set of m possible symbols. Let's say p1, p2 up to pm are the values which x can take. Once again, the entropy is defined as a minus of summation pi log pi, similar to this thing, but now we have more numbers here. That's all. This is the discrete entropy of a random variable. Of a discrete random variable, we have this entropy, and entropy is minus summation p log p, just that. Okay. And now the concept of information. What is the mutual information? So the interpretation of joint and conditional entropy is what we are going to discuss here. So H is for entropy for throughout this lecture, and now we have two random variables x1 and x2, and the uncertainty resolved by revealing the value of x1 and x2, that is the h of x1 x2. Okay, that is defined below here, but we need to look at what happens when a specific value of x2 is known. Okay, this is the general uncertainty resolved by revealing x1 and x2. But if you have a specific value of x2, that is h of x1 given x2 is equal to n2, okay, that is conditioned on the fact that the second random variable takes the value n2. Okay, the amount of uncertainty revealed resolved by that, okay, that is h of x1 given x2 is equal to n2, and that is used to define the mutual this entropy, this h of x1 x2. H of x1 x2 is just use this guy and take the average of this. The average amount of uncertainty resolved by revealing the values of x1 if x2 is known. Okay, x2 for now take the each of the values x2 can take n1, n2, etc. and then compute this h of x1 given x2 is equal to n2, and then uh, this is just a random variable, right? So it has an entropy that is known to us from the previous. So any random variable has a entropy. Therefore, this thing is totally known. This is a random variable, and this thing is totally known to us. If x, this is because this is a random variable, and take all the take the average of this thing. The average of this thing, you get the total, entropy of conditional entropy of x1 given x2. Now, the mutual information between the random variable x and y is h of x minus h of x given y. That is the amount of information y can convey about x. So if you have two random variables x and y, what is the amount of information y can convey about x? That can be interpreted using this value term ixy, which is defined as h of x, and subtract the mutual entropy h of x given y from the entropy of x. And for using this two this idea of entropy and mutual information, we can discuss what is known as a channel coding theorem. In the channel coding theorem, again, the setting is the same thing. You have a random variable x, which we input into a channel, which is a conditional probability distribution, and we get the output y. And we assume, there is one assumption here, is that each time we use the channel, that means each time we send this x through samples from x through this channel, we assume that is independent. Okay, this is an independent use, and the number of bits that can be communicated faithfully over n uses of the channel is n times c, where c is this one. Okay, this is the channel coding theorem. Channel coding theorem is the per use of the channel. If you use the channel once, how many bits of information can be sent? Okay, that is the maximizing I of xy over the distribution of x. Okay, maximize the information. So the I of xy is this thing, this mutual information. Maximize the mutual information over the distribution of x. And this is where your input distribution and how x is distributed. Maximize your input distribution is maximize your ixy under the input distribution is known as the capacity of the channel, or that is the number of bits that can be communicated faithfully over n uses of a channel. All right. So the number of bits that can be transmitted per use of a channel reliably in the limit of large n use of that. That's what the per use means. It is a asymptotic limit. You cannot expect that it happens every time, but this is the maximum which you can get reliably, which can be sent reliably as you have large and large n. Okay. So now let's look at what is the capacity of a binary symmetric channel. Okay, so binary symmetric channel, once again, x is given like this with, let's say now we have a prior probability q and 1 minus q, and 0 is flipped to 1 with a probability p, and 1 is flipped to 0 with a probability p. That is our binary symmetric channel, and we can compute this number. Okay, in this case we can actually write down and compute this number. This number becomes 1 minus h2p. Okay, bits per use, that is the channel capacity for a binary symmetric channel. So this is important. This number c is equal to 1 minus h2p is important for us, and yep. So this number is important. The capacity of a binary symmetric channel is 1 minus h2p bits per use. And now we have noticed that BPSK with direct detection or BPSK with Dolinar receiver both forms a binary symmetric channel, right? So we can look at the um, capacity of these channels. Okay, once the same setting, BPSK with the Dolinar here, and we know the TPM which we have discussed with P is equal to this is the error probability, minimum probability of error, and the channel capacity for the BPSK is 1 minus H2P, where P is now this number. Okay, similarly, if you have Homodyne, okay, Dolinar and Homodyne is what we discussed. For Homodyne, again, once again, it's a binary symmetric channel, and P is given by this function, and once again, the capacity is the same. 1 minus H same means H2 of P, where P is this number. Form of the capacity, the formula for the capacity is same because it is binary symmetric channel. Now, what exactly determines a channel P of y given x? Okay. So here, what happens is, let's say by our BPSK situation again, alpha and minus alpha are being sent through a channel. There is some loss happening here, okay? And here in this talk, we are mostly talking about loss in the noise as loss, but that's not the only case, okay? But there are different kinds of losses and different kinds of channel arising from that. But for most of uh, this course, we are going to deal with only loss, and the modulation, the transmission medium, and the receiver together. So we have the modulation here, then we have the transmission medium here, and then we have a receiver. Okay, so the two main examples we have seen are Dolinar or Homodyne. All these things together, this part, everything together is forming a channel. Okay, so that is what our channel P of y given x. And for this channel, we can write the TPM. For both of them, of course, this is binary symmetric channel, but not necessarily binary. Any channel, the mode choice of modulation, the medium, and the receiver, these whole things together is known as is the channel. For us specifically, we have seen just the Dolinar and Homodyne. Of course, you can also take the direct detection as well. And here, this part. So we have the modulation happening here, the physical medium and the noise appearing here, and the receiver here. All these things together. Receiver means you have a, you know, decision rule and a measurement basis and a decision rule. All these things together is the channel. Okay, now how does the error rate and channel capacities compare? Okay, so here if you had the n is your mean photon number, let's say for the BPSK, alpha and minus alpha are being sent, and let's say you have a very high intensity light, so you are assuming n is becoming larger and larger here, then you can see that the probability of error becomes smaller and smaller. For the Homodyne, the Kennedy is something which we didn't discuss. That is another receiver design. We have discussed the Homodyne, the probability of error for Homodyne and minimum probability of error. That's the theoretical minimum. That is P. That is this one, and then Homodyne is this one. There is another well-known receiver known as Kennedy receiver that we didn't discuss in this talk, but that also had all these probability of errors reduces and approaches zero as n increases. At the same time, if you look at the channel capacity, if you look at this sigma is equal to e to the power minus 2, and that is your coefficient on that variable on that probability of error, that is the sigma. And if you can see that as n increases, this number decreases. That means e to the power minus n to n increases means it goes this way. That means your n is decreasing there. Okay, so n increases means you are going this direction. Okay, as n increases to infinity, you can see that this channel capacity, the capacity is also increasing. It's almost becoming 1. Okay, so per use you can never achieve 1, but as n increases, you can see that all these receivers really become very good. It almost approaches 1 here, the both Dolinar and Homodyne. All right, so for BPSK, Dolinar is a very good, BPSK plus Dolinar gives you very good channel capacity. And Jack, do you like to take a break here, or do you want me to continue a little bit?
I think let's maybe continue a little bit, and then when we get to joint detection, maybe we'll take
Sure.
another short break.
Okay, let's look at a little more theory, and after that we'll go to Jack for numerical visualizations. And for this, let us look at one-Neumann entropy. What is the before that? Initially, when we started, a pure state was just a vector, right? Now, that vector gives a rank 1 projection, which is written like this. This is a Dirac notation for a rank 1 projection. If you have seen linear algebra, this is if you have a vector, let's say C, then C with the C bar transpose, you get a matrix, right? The vector C and the vector C bar transpose. If you multiply these two vectors together, this is a column vector and this is a row vector. If you multiply them together, you will get a matrix, right? And that matrix is known as the density operator associated with the pure state. Now, you can actually create more general states which are known as mixtures of pure states. These are just convex combinations of this pure state. That means you have some probability distribution pk and you just combine CKs, your pure states, using this probability distribution. These convex combinations of pure states are known as a general density operator. And these are trace one operators and positive semi-definite operators. So positive semi-definiteness, it means in this case just eigenvalues are positive. All the eigenvalues of this matrix or the operator are positive. Okay, these are all self-adjoint operators and the positive, all the eigenvalues are positive. That means that is the property that rho greater than or equal to 0. That is positive semi-definiteness. And positive semi-definite operators with the unit trace are known as density operators. And these are the general mixtures of pure states by something known as spectral theorem. The spectral decomposition says that if you take any state rho, that means any density operator rho with the positive trace class operator with unit trace, then you can actually decompose them using its eigenvalue distribution and the eigenvectors. These are the eigenvectors and these are the corresponding eigenvalues, and these eigenvalues all sum to 1 because the trace is 1, and the one Neumann entropy now is defined for any density operator rho, which is the one Neumann entropy is the h of this distribution. The entropy of this lambda I, this is a probability distribution. Summation lambda I is equal to 1 means this is a probability distribution. Therefore, it has a Shannon entropy. The Shannon entropy, which we saw at the beginning of this session, of this eigenvalue distribution is known as the one Neumann entropy of the density operator rho. Okay, so now onwards, when I say a state, it need not be a pure state. It can be a density operator as well. And for a pure state, you can actually see that the pure state is what? The lambda i's are 0 or 1, right? The eigenvalues of a pure state are, if you take it just like this, a pure state, the eigenvalues of these states are this is a projection, right? For this projection, the eigenvalues are either 0 or 1, okay? So, the one Neumann entropy of that state, which is the Shannon entropy of the distribution 0, 1, that is equal to 0, okay? Therefore, so what we have learned in this is that if you have convex combination or a probabilistic, combination of pure states, you get mixed states. They are known as, they are called either density operator or mixed states. And the one Neumann entropy is the Shannon entropy of the eigenvalue distribution. And for a pure state, that is 0. Okay. Now, there is one more notion of the capacity in quantum theory, that is the Holevo capacity of pure state alphabet. Let's say we have x is taken as 1, 2, and we have a quantum channel here, and let's say the output is cx, okay, and let's say that c1 c2 the scalar product is sigma, okay. The Holevo capacity is the one Neumann entropy of the state ensemble. Means that the one Neumann, you consider the all possible C1 and C2, and if you have the prior distribution for C1 to be P and prior distribution for C2 to be 1 minus P, and you mix them like this, okay? So this is, as we discussed, this is a pure state, and this is a mixed state now, and this mixed state has an entropy, right? Has a one Neumann entropy, right? That is S of rho, that mixed state. That means you consider the eigenvalues and then look at the Shannon entropy of the eigenvalues of this mixed state, okay? Now, among all the possible priors, okay, you mix C1 and C2 using all the possible priors and consider the one Neumann entropy and pick the maximum value, okay? Then maximize the one Neumann entropy of the mixtures, all possible mixtures of C1 and C2. the maximum value of that von Neumann entropy is known as the Hollow capacity. And if C1 is written like this and C2 is written like this, um, in terms of sigma, okay, in terms of the scalar product between C1 and C2, then you can see that this is the maximum of the von Neumann entropy of this matrix. I'm just writing this matrix. What is this matrix? This matrix will look like this. The P times C1, C1, 1 minus P times C2, C2, this matrix. This will look like this, and since you have a 2 by 2 matrix here, you know how to compute the eigenvalues, and then now we can apply the von Neumann, or we can apply the entropy formula to the eigenvalue distributions, and then that is how you get the von Neumann entropy, and then maximize all the p's. Okay, those numbers you maximize all p, you get the Hollow capacity, that is C infinity. And this expression for Hollow capacity, this is actually the binary entropy, okay, of this p. This take p is equal to 1 minus sigma or 2. That is where this is maximized actually, okay. So the binary entropy 1 minus sigma over 2 is the Hollow capacity when you have C1 and C2 with, separated in scalar product with sigma, okay. And this formula is also important for us, the Hollow capacity. So now we discuss what is photon information efficiency. So that means that given the number of photons, so number of photons n, how much bits per photon, okay, can be sent. So given so that is what is known as the photon information efficiency. So if you have n photons, your budget is n photons. Now what is the bits per photon? How many bits per photon can you send for different kinds of channels? We can see that the Dolinar here is like this. That is with the perfect probability of error. That is some minimum possible probability of error. With that, we get a very good, photon information efficiency. But the Hollow capacity, you see, this is much, much, much bigger than what we can achieve using even with the best receiver model, for BPSK. This is all for BPSK actually, and for various Homodyne, Kennedy, and Dolinar. Okay, all these things. There are other channels which we have not discussed. But the point I want you to notice here is that the Hollow capacity is the maximum possible capacity. Okay, for any quantum system that is much, much, much larger than any known receiver design. Okay, so that is why there is a ideal limit for this information transmission, but we don't know how to achieve that, how to build a receiver which can achieve that. So even the best receiver for the BPSK is not able to achieve the Hollow capacity. Uh, that is a very interesting question. Build better and better receiver, and the channel design, the whole modulation, medium, and receiver design together form the channel. We don't know a channel which goes closer to Hollow capacity. Okay, that's a very interesting problem in this field. Okay, now I think we should go to Jack and discuss a little bit about linear optics, and then
Yeah. So while that happens, there's a question in the chat about some like an interest in textbooks or reading about this quantum information theory. So I'm gonna post a link to an archive paper right now, and I can go find some books later, but there's ones from like Serafini that are really good. In general, so like what we're talking about right now runs at a deep intersection between um, Gaussian quantum optics, which is really like the quantum optics that's relevant for optical quantum computing and things like that, as well as general information theory and communications. So I think to me, there's no like single textbook or anything that is kind of the best to reference here. There's a lot of information dispersed across different things. But the paper that I'm gonna post in the chat, or sorry, yeah, let's see, the archive post. Do I share this with everyone? There we go. This Gaussian quantum information does a really good job addressing a lot of what we talked about here, but setting it up from even a more like rigorous background. And they discuss some of the applications here for things um, like receiver design. The other thing that you could start to look into are papers from Halevo, which actually, if you just go to like the Wikipedia for, let's see, Halevo theorem, post this. Let me post this in the chat as well. So some of the links from there will be helpful. Halevo's theorem is kind of like the impetus for a lot of this motivation, right? Where you are in a regime where you have this classical quantum channel and you're asking the question of how do I consider the quantum state that I'm using to maximize the classical information? So there some seminal works from that. Oh, the mean photon bits per photon is less than 1 megagraph. So the question was why, when the mean photon number per mode is greater than 1, the bits per photon is less than 1 in the graph. So think about it this way. If you are doing, this is specific to binary symmetric channels. Um, so, sorry, not binary symmetric. In this case, you're doing a binary modulation. So you're only sending 1 bit per channel use there. And so if you're sending many, many photons, then you're still capped at that 1 bit per channel use. So now you're going to be way less than 1 bit per photon. Like let's say you have a really strong laser and you're going a short distance. So you have, a billion photons. And during that time period, you're either going to see a photon or not. You're still only getting that 1 bit, but now it's way less than 1 bit per bit per photon. So I answered that one. Um, yeah, that's actually, so there's an anonymous question. Can we have a WhatsApp group or something similar for this to connect to like-minded people and learn and grow together? I think that's a really good idea. I know there are some Discord channels out there, and maybe at the very end of this talk, we can try to find some of those. So I'm gonna mark that as answered for now. But yeah, I like that idea. I know there's some good Discord channels out there and perhaps other things, but um, yeah, okay, we'll continue on this. Let me share my screen now. Okay. And Tiju, can you just confirm that you see my screen?
Yeah, I think yes, we can see yes.
Okay, okay. Let me get the laser back up, spotlight. Cool. I'll turn my video back on, sorry. Okay. Let's see. Sorry. Okay, so linear optics. So as we've been talking about, we want to really decide how we can best control and manipulate the state prior to the actual photo detection event. Because once we get to photo detection, there's not anything more we can do. It's a purely classical problem, and uh, the the information processing inequality says that we can't do any better, right? So we want to use the unitary properties that preserve the states to prepare before detection the best available state. Um, the key resource that we have in optics is the beam splitter. So for coherent states like what we've been working with, the operation of the beam splitter is a unitary operation where it's this general 2 by 2 unitary. So you take 2 modes in, 2 modes out, and you can transform the coherent amplitudes of each. So if we call it U as this beam splitter, and we act on alpha 1 and alpha 2, so each of them being modes coming in, you can think about this physically as like 2 different lines coming into a beam splitter, but it doesn't have to be that case. You can also imagine that if I have two states that are adjacent to one another in time, by that I mean imagine that you are a receiver and alpha 1 comes to you first during some, say, 1 nanosecond period, and then immediately after alpha 2 comes to you during another 1 nanosecond. You can design systems that will implement a general unitary transformation like this beam splitter. But the easiest way to think about it is what it intuitively looks like here. You have a physical cube, and you have this evanescent coupling between these two sides, and you're transforming 2 input states into 2 output states. This U is parameterized by, you can think of it as an transmissivity angle in a phase. There are quite a few different ways to write this transformation, but what you need to know is that it has a determinant of 1 and is this general 2 by 2 unitary. So if we take alpha 1 and we choose some theta and phi, then we're going to transform beta 1, which will be some linear combination of alpha 1 and alpha 2, and beta 2 will follow the other. So if we were to write it out in terms of, instead of theta and phi, if we write it out in terms of the transmissivity, which is defined as cos squared of theta, and phi still being the angle, then the input-output relations look like this. The output beta 1 is going to be root of the transmissivity of alpha 1, and then a phase added on to the complementary portion of alpha 2. And beta 2 will be, similar to this, but with a different phase angle or a slightly different phase, and the transmissivity is flipped. This is useful in a few different applications. So this general form can be used for a lot of applications, but I'll list a few below. So destructive interference is relatively straightforward here. So kind of like how we did in the Homodyne system, we're bringing in some signal alpha, and then we might say we have a local oscillator here. So if we choose this to be minus alpha, then when we get this output here, or sorry, let me back up. So if I choose this minus alpha to kind of be my local oscillator, then whatever this input here is will determine how much of my signal is going to be here in this output arm versus the other. So I'm choosing a transmissivity of 50% basically. So this is a balanced beam splitter with no phase. And in this case, I get a perfect destructive interference. If you flip this also to be an alpha, then you're going to get a splitting where it'll be like half and half. But yeah, it's phase dependent and amplitude dependent. A pure phase is what it sounds like. So you can induce a relative phase shift on one. So in this case, alpha goes to alpha, beta goes to beta with an additional phase. And importantly for a lot of receiver designs is this idea of nulling or displacement. So recall that the Dolinar receiver was the one that we said does the best job for discriminating between two binary phase shift keying states. So if you have only two signals, the Dolinar receiver is the best you can do symbol by symbol. Well, what it's really doing in many different adaptive time steps is it's applying a local oscillator with a very controlled coherent amplitude beta, where this is a really, really strong local oscillator, and it's a very, very high transmissivity system. So alpha comes through basically unimpeded, but we're picking off a very small portion of this beta over root 1 minus eta, and we're going to effectively induce a displacement of alpha plus beta. So in phase space, we are physically shifting or displacing the coherent state input output. So the Dolinar receiver works like this by adaptively choosing this beta. So this is an important operation. Let's see. But one thing we can consider also is that we don't necessarily have to just have the local oscillator be the second input there. What if we want to do something where we take two different modes, like I mentioned, either two spatial ones or two temporal, one coming right after another, and we want to act on them together to get something called joint detection. So we're choosing to have a receiver that acts on multiple symbols and multiple channel uses collectively to achieve a higher capacity than symbol by symbol. So our system is relatively the same as before, where we're sending a series of coded transmissions. In this case, it's 0 or 1 is the binary, the raw data. We can encode that using some forward error correction code into this ternary state, 1, 2, or 3. And each of these you can see is coded to represent the original binary values. So this 3-bit binary 0, 1, 0 is transformed. This is all digital. This is all just happening in a computer. You're trying to figure out how to write this information. This 0, 1, 0 is transformed to 1, 3, 2, 1, 3. And this 0, 0, 1 is transformed to 3, 2, 1, 3, 2. And lastly, this 1, 0, 1 goes to 2, 1, 3, 2, 1. So it's abstract. Don't worry about it too much right now. Just know that I'm choosing this digital transformation. But now when I need to embed it into the channel, instead of sending, say, alpha minus alpha and then like maybe a vacuum, I'm going to choose it such that x1 is now two channel uses of alpha. x2 corresponds to an alpha and a minus alpha, and x3 corresponds to minus alpha and an alpha, all with the discrete ordering. So that way you can, these are separate. They're different things. Now it goes through a lossy channel as before, so we get this damped down version of the coherent state, but each of our code words still has its associated coherent amplitudes. And now I'm going to put both of these channel uses into a beam splitter, and then in one arm, we'll do direct photo detection. So we're just searching for the presence of a photon or not, and then a Dolinar receiver on the other end. Now, if you were to work out the exact probability matrix of this, what you would find is that it looks like this. So if I send x1, there's some probability of it being decoded as 2 or 3. X2 can only be decoded as 2 or 3, and x3 will always, or will also be as x2 or x3. So now you have this transition probability matrix, and you can assign prior probabilities. To kind of match the symmetry, what you'll do here is you'll put probability of P associated with X1, and then an equal probability for PX2, PX3. And you can see that's just comes from the symmetry here. And if you were to then calculate the mutual information, knowing all the things that you've just found, so you now have the marginals and you have the conditional, you can calculate this mutual information. And then if I normalize it by the fact that I'm using 2 channel uses, and then compare it as my mean photon number goes really low, so in the photon star regime, what you'll see is that this rate of this receiver actually outperforms the symbol by symbol capacity that's best achieved by a Dolinar receiver. So we're actually getting this super additivity that comes out of the joint detection here. And in some way, you can think about it as like compressing the energy from multiple pulses together. That's not exactly a direct result of what it's doing, but it can be helpful to kind of intuit that way. And so what we're saying is that in the weak limit, in the limit where you have very little information to begin with, by instead of going symbol by symbol and just using one channel use at a time, you can actually get an improved capacity by going through and performing this collective measurement operation. So instead of putting this joint detection receiver here, imagine instead that you put a Dolinar receiver alone, and it just looks at each of these 2 channel uses, oops, and then tries to make a guess. So it might say it might guess alpha alpha, and then you would say, okay, that was X1, or it might guess alpha alpha here as well, and then you would still guess X1, but you'd be wrong. That's not what we're doing. We're doing this joint measurement by combining the 2 states into one larger state. Now, just like how we don't know how to design ideal receivers for an arbitrary codebook, we don't know how to design joint detection receivers that can maximize our capacity, but there are some examples. So one is a joint detection receiver known as the optical green machine. So it's a structure designed for a receiver that takes a BPSK encoded Hadamard codebook. So this codebook looks like this. It's all alphas and minus alphas over power of 2 number of channel uses. In this case, it's 8 channel uses. And a code word is selected from this codebook. So this is a 3-bit 8 mode codebook here. So this column of all pluses would be all alphas. And then each time you see a plus or minus, that just corresponds to plus or minus alpha. You transform that with a series of beam splitters that perform a Hadamard-Walsh unitary transform on the input codebook, and it transforms it into a pulse position modulation output, where the energy or the coherent amplitude present in that pulse position modulation is determined by the size of your codebook here, right? So I'm taking all of these BPSK inputs, they're coming, in this case, 8 of them. I'm transforming it such that before detection, all of my signal is now present in a single time slot. So I can deduce exactly what the code word was. So I'm having this unambiguous discrimination, right? Like the only error that can happen is that I don't get a detection event here, and then I say, okay, it was an erasure. But in an ideal system now, there's no probability where I get this code word here, but I guess the wrong code word. So it makes the transition probability matrix pretty nice here. It's this M erasure channel where I have this probability of correctly getting it. I have this probability of erasure, and there's no other possible outcomes. So it has a nice symmetry to it. And if you go through and calculate the capacity, we don't have to go through all the steps here, but you can calculate the entropy of your Y output. So it's going to have this nice symmetry of M terms that are all identical. And then you have your erasure channel. And then you can also calculate your conditional entropy, which in this case, because each of the channels is symmetric, or each of them is equivalent, but with just a different input, it's just a binary erasure channel in each one. And you see that you get this capacity 1 minus e to the minus mn log 2m. And so if you were to plot this, now what you would see is that for progressively larger systems, By that, I mean you're changing the number of modes to go from 2 modes to 4, all the way up to say something like 1,000, a little over 1,000 modes. And then you plot your photon information efficiency. As you go deeper and deeper into the low mean photon regime, you can get this higher curve, which is corresponding to the photon information efficiency. So for m equals 2, the 2-mode one, which is really just a beam splitter, it's hard to see, but it just curves, let's see, right around here. So it's just this really yeah, weak system. It's not that impressive. But if you go all the way to 1,000 modes, then you see that its capacity is not very good when you have this relatively strong signal, but when you get to really weak mean photon numbers, you get this huge superadditivity. And you can compare that to these dash lines down here. So the dash line is the Dolinar receiver for all of these BPSK Hadamard code words. So this would be like the classical symbol by symbol detection bound, and you can see that there's a gap. In this case, it's closing in on an order of magnitude gap in this regime here. And conditioned on where you are in the mean photon regime, there would be a different sized green machine receiver that would give you the highest photon information efficiency. For reference, also, this blue dashed line here is Homodyne detection, and below that still further is a heterodyne, which is one that doesn't require phase stabilization with your signal. So yeah, all of these you can see that there is a superadditivity and it's a structured design, so you can choose the right size depending on your received mean photon number. So this is a structured design for a superadded receiver. However, there is a gap. So this black line here is the Halevo capacity for the BPSK channel. And you can see that, none of these green machine receivers touch this. And in fact, there's actually a gap that's growing. So while this is a structured design that can give us superadditivity, it does not give us the ability to get to the Halevo capacity. So there still is more that we can do just based on the pure nature of the light that we're using to modulate, which is really where this Halevo capacity is coming from. It's just saying if I have a given set of modulations that are allowed, in this case, coherent modulation, what's the best I could possibly do? And so it's a combination of your modulation and your receiver. And in this case, we don't know a general structured receiver design that can get us here without. There are some examples with like perfect transduction and a quantum computer, but in reality, we just don't know any designs that get us there. So that kind of wraps up my portion here. We're going to go once more back to the collab to just do a few more quick things there. So let me switch over to that and then share my screen. Okay. Can we get confirmation that my web browser is visible?
Yeah,
to
yeah.
you?
So
Okay. Sweet. So we're going to just do two quick things here. One, if you scroll down to where we left off before, we say section 2 starts here. We're going to add in the mutual information definition. So this is just a useful definition for numerically computing the mutual information, given that you have a transition probability matrix and a marginal, and it'll calculate that for you. And then also the binary entropy value. This is something that pops up quite often, so just having a nice little definition for it to plug in. So we will define that. And then next, we're going to try to numerically determine the capacity for a homodyne with BPSK. And so we're going to do that by using the same system we did before, where we're going to sample the homodyne output for a given alpha value. And then we're going to just construct our transition probability matrix and get the mutual information out. So I think this might be a little slow if you leave it at the 10,000 that was on before. So let's just go with 1,000 and see how long that takes. Okay, great. There we go. So you can see that what it printed out here was this conditional probability matrix, the transition probability. So if I'm given x1, the probability of decoding it is 97.7%, and it has this crossover of 2.3%. And because this is a numerical simulation, it's not perfect. So we have a slightly different one for y2, even though it should be, or sorry, x2, even though it should be symmetric. So if you pump that number up beyond 1,000, you'll get closer and closer to the same value. And then it gives us an associated mutual information, which is really our capacity of the channel. So You could try this with choosing different alphas, sampling it a larger number of times. And this is just a way that you can show that if you have a conditional probability and you have the marginals, that you can do this calculation to get your capacity. And the last thing we're going to do is just a quick plot just to kind of show plotting these capacities against each other. So there's no modeling here with strawberry fields, but if you want to, you could go in and try to model strawberry fields with different values of the mean photon number to try and have it line up with the capacity that you see here, this thresholding capacity for Homodyne. But if we just run this one below, we should get out this plot, which shows you the Alevo capacity for BPSK and the different green machines. And what we're doing is we're really just plotting the capacity as we've defined them throughout the slides so far. We've got a lot of analytical solutions for the capacities. So we have our Homodyne capacity, Dolinar, Alevo, heterodyne, and then this kappa ray is it's going to be the green machine ones for various sizes of modes. So yeah, I think that's all we have here for the code. So I will hand it back over to Tiju to kind of start to wrap us up here.
Very good. Thank you, Jack, for the nice, visualizations, and I hope people will make use of the resources provided. And let's wrap it up. Let me share my screen. So is it visible?
Yep.
Very good. So we have been looking at the optical communication setting, and let us have an overall look at what we have been doing. So we started this talk with saying that information can be converted to classical information can be converted to zeros and ones. We have zeros and ones, and then encoder. We did not discuss about this thing. We add some redundancies here, and we code this thing. For example, there is an encoding scheme here for each 0 and 1. We are repeat. I think this is repeated. I think, yeah. And coded transmission goes through the channel, and then we have this PO by given X, that is the channel in which all these modulation and modulation and the physical medium, the receiver, all these things happen, and then we get an output. And in the output there may be errors because of the receiver design we have here. And those errors, for example, if 1001100 was sent, the third one, let's say here it was 0, and here it became 1, let's say, okay, that was a error. Similarly, there might be some other errors, and in the terms of this alpha and minus alphas, what has been sent is that instead of 1 we send alpha, instead of 0 we send minus alpha. That is what is happening in the channel here, and some of them flip. And also in the loss, if you have an eta loss in the channel, the output might be square root of eta times alpha and minus of square root of eta times alpha. It doesn't matter much. We can still make out what is alpha and minus alpha. We used our best receivers and we get the output. And this is how this communication net happens here. And this picture is a more sciencey picture of what we have been showing you from the beginning. Okay, we have a transmitter and a receiver and a medium in between, and the coded messages goes into the transmitter, goes into the channel, and where the modulation is there and the noise is there, and there is a receiver, and then we get the output. This is what we were discussing, and what we have learned. Okay, we have learned the fundamental efficiency of encoding the information in a photon is a function of how we encode and how we choose to detect. So these are the two main things: how we encode, how we choose to detect the information. These two things are most fundamental in the efficiency with which we can send and receive data. And quantum physics, because we are using light and light is quantum, there are some there exists some noise inherently in the system. There are some noise. We cannot deterministically figure out what has been sent. Okay, so quantum physics tells that there exists some amount of noise in the form of detection. In any form of detection, you can choose the best receiver you have. For example, the Dolinar, which we had for BPSK, but still, it is not achieving the best capacity which we can get. So that's what I was discussing here. Neither of the detectors, Dolinar or Homodyne, achieves the optimal performance with any of the encoding formats. When we go to communications, even the Dolinar detected best theoretical receiver is not the best possible receiver that can maximize the rate at which we can communicate information. That is what we have seen in the joint detection, isn't it? The joint detection receivers perform better than symbol by symbol detection. That's another thing which we learned from the last part where Jack explained the theory. A general problem. So this field is wide open. Okay, a general problem of interest is how to best position the information bearing photon so that we can improve the capacity. Okay, so the maximum is in terms, it can be based on the number of photon, based on your efficiency, based on your photon information efficiency or the capacity. So depending on your constraints, how to align your photons or what all manipulations you can do on your photons so that you can maximize your capacity. And with that, we stop this course here. Thank you. Thanks a lot for your attention. And please do this. Don't go away right now. Please go on and do the survey. And see you all soon again.
Wonderful. Thank you, Tiju and Jack. As you exit out of the webinar, you will be redirected to our post-course survey. Please take a moment to take that. And then in the coming weeks, we will have the recording and the slides and resources available on our website. I'll also get an email out to all attendees with that information. And then with that, I'll go ahead and end the webinar. Thank you, guys.